100 ocean facts that sound fake, but will put you to sleep in minutes. If we dried the ocean, the remaining salt would form a wall 280 kilometers wide around the equator. There is a way of imagining the ocean that we rarely attempt. Not as a shimmering surface or a dark depth, but as a container. An extraordinarily large container, overflowing with salt water that has accumulated and reorganized itself over billions of years. And when you start thinking about the ocean this way, as something that contains things, one of the first questions that arises is, what exactly is it holding? The simplest answer is water. About 1.335 billion cubic kilometers of water. It is a number so large that the brain hesitates before trying to process it. But within that water, dissolved so completely that you cannot see, feel, or easily separate it from the rest, exists salt. A quantity of salt that defies any reasonable comparison with everyday human experience. The oceans contain approximately 50 quadrillion tons of dissolved salt. 50 followed by 15 zeros. And if you try to visualize what that means in concrete terms, you arrive at something that almost seems fantastic. If all the ocean's water evaporated tomorrow, what remained would be a solid layer of sea salt covering the floor of every ocean basin, every continental shelf, every tide pool. This layer would be enough to build a wall 280 kilometers wide around the entire circumference of the equator, high enough that people on top would never see the ground. It is almost impossible to contemplate, and yet this salt is there now, invisible, perfectly dissolved, while you breathe. The immediate question this image raises is, where did all this salt come from? The answer is not from a single place and did not happen all at once. Ocean salt has accumulated over a geological period so long it makes the concept of human antiquity seem like a whisper. Some of it came from rocks. Rain is slightly acidic by nature, which means that when it falls on rocks and drains into rivers, it dissolves minerals along the way. These minerals travel as charged ions, descending rivers for hundreds, sometimes thousands of kilometers, until they reach the sea. Sodium arrives this way. Chlorine arrives another way, through undersea volcanoes and hydrothermal vents on the ocean floor, which release gases and minerals directly into the water from the planet's own interior. And unlike rivers, which continuously pour new amounts of salt into the ocean water evaporates relatively slowly and the salt stays behind. It does not evaporate along with the water because the bond between the sodium and chloride ions and the water molecule breaks when evaporation occurs. The rain that falls back onto the land is almost entirely pure. The salt stays, and over hundreds of millions of years, the salinity of the ocean has gradually increased, reaching the level of approximately 35 grams of salt per liter of seawater that we find today. This process, however, is not out of balance. The ocean does not get saltier indefinitely. There are mechanisms that remove salt from the water as well. Some of it is captured in marine sediments. Some is incorporated into organisms that build shells and skeletons. Some is expelled back into the Earth's crust in subduction zones, where tectonic plates sink and are reabsorbed by the mantle. It is a long, slow cycle, but it is a cycle. The ocean is in a state of dynamic equilibrium with the planet, constantly exchanging salt with the rocks, the seafloor, and the atmosphere. The ocean holds 1,000 times more heat than the entire Earth's atmosphere combined. When we think about Earth's climate, we tend to think about the air, the wind, the clouds, the storms that pass over our heads. The atmosphere is what we experience directly every day. It is what we feel when we leave the house and gauge whether we need a coat. It is natural, then, to assume that the atmosphere is where most of the planet's thermal energy is stored. But this is one of the greatest shifts in perspective that ocean science offers. The atmosphere, with all its wind and weather and temperature, is almost irrelevant as a heat reservoir when compared to the ocean. The ocean holds approximately 1,000 times more heat than the entire atmosphere above it. To understand why, it is helpful to start with a simple property of water that anyone who has ever cooked anything knows intuitively. Water is extraordinarily difficult to heat up and extraordinarily difficult to cool down. Scientists describe this by saying that water has a very high heat capacity. What this means is that you need to add much more energy to water to raise its temperature by 1 degree than you would need for almost any other common substance. Air, By contrast, heats and cools with relative ease. Add a little solar energy to the air and it heats up quickly. Remove that energy and it cools down quickly. Water acts much more patiently. It absorbs energy slowly, holds it for much longer, and releases it gradually. Now multiply this property by the volume of the ocean. The ocean is immensely deep. The average depth is about 3,700 meters, with trenches that descend far beyond that. And all this water, from the surface to the deepest and coldest layers, is in continuous contact with the heat entering the planet from the sun and the internal heat emerging from the Earth's core itself. Over time, the ocean has absorbed an amount of thermal energy that the atmosphere simply does not have the capacity to store. The implications of this for the climate are profound. The ocean acts as a gigantic temperature regulator for the planet. Without it, temperatures on the Earth's surface would swing much more extremely than they do now. Days would be much hotter and nights would be much colder. Seasons would be more extreme. Coastal regions of the planet enjoy milder climates than continental interiors precisely because the nearby ocean absorbs and releases heat much more steadily than dry land. Port cities rarely experience the freezing winters or scorching summers that can occur in the center of large landmasses. The ocean buffers. But there is another dimension to this heat-storing capacity that has become increasingly relevant over the last 2 centuries. As human activity increases the concentration of greenhouse gases in the atmosphere, more solar energy is trapped within Earth's climate system instead of being radiated back into space. Where does this extra energy go? To a large extent, it goes into the ocean. It is estimated that the ocean has absorbed more than 90% of the excess heat generated by climate change in recent decades. This means that, in many ways, the ocean has been functioning as a climate buffer. Its enormous thermal capacity has slowed the pace of changes that would otherwise be felt much more intensely on the surface. The ocean is blue because water absorbs long-wave colors like red and reflects short-wave ones like blue. There is a question that children often ask and that adults answer automatically, as if the answer were obvious. Why is the ocean blue? The most immediate answer most people offer is that the ocean reflects the sky. It is a reasoning that seems intuitive. The sky is blue, the ocean is under the sky, therefore the ocean looks blue because it acts like a mirror. This explanation has the virtue of being understandable and the disadvantage of being, for the most part, wrong. The color of the ocean comes primarily from within the water itself, from a physical property of the H2O molecule that most people have never needed to consider. White sunlight is not a single thing. It is a mixture of all wavelengths of the visible spectrum, from red and orange at the lower frequencies to blue and violet at the higher frequencies. When this light comes into contact with water, something happens that does not happen with most other transparent materials. Water does not let all wavelengths pass with equal ease. It absorbs them in different ways depending on their frequencies. Red disappears first. Only a few meters below the surface, most of the red light has already been absorbed by the water molecules. Then goes orange, then yellow, then green. At depths ranging between 10 and 30 meters, depending on the clarity of the water, the remaining color spectrum is dominated by blue and violet. These short-wave, high-frequency wavelengths are the hardest to absorb and travel deep through the water before finally being dissipated. And they don't just penetrate deeper, they are scattered. When blue light encounters particles in the water or is reflected by the H2O molecules themselves, it scatters in all directions, illuminating the water column from within. The result is that the water appears not just to transmit blue but to emit it, as if the water itself produced that color. This is why a deep, clear ocean has a deep and almost uniform shade of blue. It is why shallow waters over a light sand bottom tend toward turquoise and green. The bottom reflects some light and the shallower depth means enough longer wavelengths still remain to mix with the dominant blue. And it is why water in a glass looks colorless. The thickness of a few centimeters is completely insufficient for the absorption effects to become noticeable. You would need a column of many meters of pure water to start seeing the blue visibly emerge in a container. This property of water has implications that go far beyond the color of the ocean. The way sunlight is filtered as it descends through the water column determines at what depths photosynthesis is possible. Phytoplankton, the microscopic organisms that produce most of the planet's oxygen, depend on light to grow. The zone in which light penetrates sufficiently to sustain them, called the photic zone, corresponds approximately to the first 200 meters of water. Below that, as the blue is also finally absorbed, everything goes dark. And in the abyss, hundreds or thousands of meters deep, there is absolutely no sunlight. It is a darkness so complete that the organisms living there have never seen any wavelength of the visible spectrum. About 70% of Earth's freshwater is locked in polar ice caps that float on or border the ocean. Water is synonymous with the ocean for most people. When someone says water, the image that arises is blue, vast, and salty. But there is another form of water on the planet that is so monumental in its scale that it is sometimes difficult to incorporate into our mental map of the Earth. It is frozen freshwater, the kind that does not flow through rivers, does not fill lakes, and does not fall as rain. It exists in a solid state, piled in layers over millennia, sitting atop Antarctica and Greenland and suspended in glaciers around the world. And a surprisingly large fraction of all the planet's freshwater is in this form. Approximately 70% of it. To put this in perspective, it is useful to start with the big picture. Freshwater represents only about 2.5% of all the water on the planet. The remaining 97.5% is salt water in the oceans. So freshwater is already a minority. And within that minority, the largest slice is not in the rivers that feed cities, the lakes that sustain ecosystems, nor the underground aquifers that supply wells. It is frozen. It is in the polar ice caps. This distribution is both staggering and practically invisible to most people living far from the polar regions. Antarctica is the largest fraction of this stock. This continent, buried under a layer of ice that can exceed 4 kilometers thick in some spots, alone contains approximately 60% of all the Earth's freshwater. It is almost impossible to visualize the scale of the Antarctic ice sheet from conventional photographs. Typical images show flat, white ice stretching to the horizon, with mountain peaks emerging here and there. But what you don't see is that there are entire mountains submerged under the ice. Complete mountain ranges, valleys, lakes that have been sealed under the ice for millions of years, isolated from all known life, forming their own microscopic ecosystems in a darkness pressed by the depth of the ice above. Greenland contributes most of the rest. Its ice sheet, though smaller than Antarctica's, is still of a magnitude that dwarfs any comparison with everyday experience. And then there are the mountain glaciers distributed in the Andes, the Himalayas, the Alps, the Rockies, and Alaska. Each is a repository of snow compressed into ice over centuries, feeding rivers that descend into valleys where human communities have grown dependent on their seasonal melting. The fact that all this freshwater borders or floats on the ocean creates a relationship of enormous importance. When polar ice melts, this freshwater goes into the ocean. This has two main effects. The first is the most immediately understandable. Sea levels rise. The amount of liquid water on Earth is approximately fixed, but its distribution between ice and liquid ocean is not. When temperatures rise and ice melts, the volume of water in the oceans increases. If the entire Antarctic ice sheet melted, the world's oceans would rise by about 58 meters. If the Greenland ice sheet melted completely, it would add another 7 meters. For most of the world's coastal cities, even a fraction of these numbers would represent an irreversible transformation of habitable geography. There is a solitary whale that sings at a unique frequency. No other whale can hear or respond to it. There is a sound in the ocean that has repeated for decades. A call that travels for hundreds of kilometers through the dark water, propagating with the precision and persistence that characterize the vocalizations of great whales. It has rhythm. It has a pattern. It changes slightly over the years, as do the voices of any living being that ages. And during all this time, since hydrophone records first detected it in 1989, there has never been a response. No other corresponding vocalization. No echo of recognition. The call travels, and then it dissipates in the dark. The whale that produces the sound sings at 52 hertz. To put this in context, blue whales, the largest animals to ever exist on Earth, typically communicate at frequencies ranging between 10 and 39 hertz. Humpback whales, whose long and complex songs are perhaps the most studied of any animal vocalization, sing at frequencies that vary widely but generally stay in the 80 to 4,000 Hz range depending on the context. Each species has an acoustic signature, a frequency at which its vocalizations were shaped by evolution, tested over millions of years of underwater communication, and refined to propagate efficiently through the marine environment. And the reason why these frequencies matter so much for communication is not arbitrary. Ocean water has specific properties that determine which frequencies propagate over the greatest distances. The 52 Hz whale sings at an intermediate point, higher than blue whales, lower than many other species. And the consequence of this acoustic positioning, according to researchers who tracked its movements over the decades, is that its call does not fit into the hearing window of any known whale species in a way that would generate a natural response. It sings and its songs cross the ocean, and from the point of view of any other whale in the ocean, it seems like no one is there. There is much we do not know about it. The animal has never been sighted. We infer its existence and its movements entirely through records from hydrophones, networks of underwater microphones originally deployed by the U.S. Navy to track submarines during the Cold War and later released for scientific use. These hydrophones have picked up its vocalization repeatedly over decades, and researchers use time differences between detections at different locations to triangulate the animal's position and trace its route over the years. It migrates. It moves with purpose. It is clearly an animal healthy enough to have survived decades in an ocean that would be hostile to any weakened creature. But its species is uncertain. Some speculate it is a blue whale with an anatomical anomaly that causes its sound production to differ from the norm. Others have suggested it might be a hybrid between species, something rare but documented in other whale groups. An animal whose vocal apparatus inherited characteristics from two different lineages and ended up producing a frequency that doesn't fully belong to either. There are also those who believe it may represent a completely different species, as yet undescribed by science, inhabiting depths that have not been adequately sonified. What is certain is that throughout decades of recording, the 52 Hz whale has remained unique, a matchless acoustic signature, and this has led many people, including scientists, to project onto it the idea of loneliness. The animal has been called the loneliest whale in the world, its situation described in almost literary terms of isolation, of a voice no one hears, of a call without an answer. Journalists have written about it with tenderness. People who have gone through periods of isolation in their own lives have written about feeling identified with it. It has unexpectedly become a symbol. Scientists tend to be cautious with this projection. We do not know if the 52 Hz whale experiences something we call loneliness. We do not know if the absence of a response at its specific frequency means it exists in total social silence. It may be that it perceives and processes the sounds of other whales singing at frequencies different from its own, even if they do not respond to its calls. The subjective experience of animals, especially of creatures whose neurology is so different from ours and whose environment is so inaccessible, is beyond what our science can reach with certainty. But perhaps what matters is not whether it suffers from loneliness the way we might suffer. The most isolated place in the ocean is so far from land that the closest humans are usually astronauts on the International Space Station. There are places in the world that are remote in the way most people imagine when they hear that word. Forests that take days to cross, islands without airports, mountain peaks that require weeks of expedition. But there is a kind of isolation that surpasses all of that. A point in the ocean that isn't ours from anywhere. It isn't days. It is more than 2,600 kilometers from any piece of land in any direction. A point where the feeling of being far away is not a metaphor. It is a coordinate. It is a geometric fact precisely calculated and recorded on a map. This point exists. It is in the South Pacific. And it has a name, Point Nemo. The name is a tribute to Captain Nemo, the fictional sailor created by Jules Verne in 20,000 Leagues Under the Sea, the character who chose the ocean as his exile, who lived below the waves precisely because he wished to be beyond the reach of the terrestrial world. The choice of name for this specific place could not be more appropriate. Point Nemo is, in geometric terms, the oceanic pole of inaccessibility, the point on the ocean surface farthest from any coast in all directions. Its coordinates were calculated in 1992 by Hervoye Lucatila, a Croatian geodetic engineer who used a computer program capable of incorporating the planet's ellipsoidal shape to find, with mathematical rigor, the most distant point from land that exists on the ocean surface. The three landmasses closest to Point Nemo are Ducie Island, part of the Pitcairn Islands archipelago to the north, Motu Nui, a rocky outcrop adjacent to Easter Island to the northeast, and Mar Island, a small Antarctic island to the south. All are approximately 2,688 kilometers away. To give a reference, this distance is greater than the one separating Lisbon from Moscow. It is greater than the distance between New York and Denver. In whatever direction a vessel departed from Point Nemo, it would take more than 2 days traveling at cruising speed just to see the first fragment of land appear on the horizon. But the most extraordinary aspect of Point Nemo is not its distance from coasts. It is what that distance implies about who is closest. The International Space Station orbits the Earth at an altitude of approximately 400 kilometers. When the station passes over the South Pacific, it is often closer to Point Nemo than any human being on dry land. The astronauts on board, floating in microgravity hundreds of kilometers above the ocean, are literally the closest people to that point in the ocean. It is a complete inversion of intuition about what it means to be close to something. Space, in this case, is more within reach than the land. The environment around Point Nemo reinforces this isolation in ways that go beyond simple distance. It is located within the South Pacific Gyre, a massive system of rotating ocean currents that circulate around a central region. This gyre acts as a hydrographic barrier. The currents around Point Nemo tend to keep the region's waters isolated from the wider circulation of the ocean. The result is that the water there is extraordinarily nutrient poor. There is almost no plankton, which is the base of nearly every marine food chain. And without plankton, there are very few fish. Marine life in this region is so scarce that it makes Point Nemo an oceanic desert, not just geographically, but biologically. The ocean floor in this region is approximately 4,000 meters below the surface, and the average water temperature is about 7 degrees Celsius. It is a cold, dark, biologically silent, and immensely distant place. And yet it is visited with some regularity, not by explorers or scientists, but by gravity and trajectory. Because Point Nemo is so far from any inhabited coast, the world's space agencies use it as a dumping zone for debris from satellites and spacecraft re-entering the atmosphere. When an obsolete module or a decommissioned satellite needs to be deorbited in a controlled manner, engineers calculate its re-entry trajectory so that the fragments that survive the burn fall in this remote area. There is a cemetery of space hardware on the ocean floor around Point Nemo. Entire space stations, including Russian Mir versions and segments of the ISS itself when it is eventually decommissioned, are slated to rest here. Underwater, rain creates a noise so intense it can temporarily blind the sonar of some cetaceans. There is a version of the underwater world we tend to imagine as silent. Films and documentaries contribute to this impression, replacing the actual sound of the depths with soundtracks carefully composed to induce serenity. The idea of the ocean as a quiet space is seductive and, to our ears above the surface, has some basis. The sounds of the terrestrial world do not propagate well into water. But inside the ocean, the reality acoustic is radically different. The ocean is full of sound, full of pops, hums, clicks, and songs. And among the most intense and unpredictable sources of sound in the marine environment is rain. When rain falls on the ocean surface, seen from above, it produces only a series of concentric circles and a damp whisper. But what happens on the underside of that surface is completely different. Each raindrop that pierces the surface creates an air bubble. This bubble collapses in fractions of a second, and as it collapses, it produces a high-frequency sound that propagates through the water with considerable efficiency. Multiply this by hundreds of thousands of drops per second during heavy rain, and the result is a broadband noise that can completely saturate the underwater acoustic environment. This noise is not just uncomfortable for cetaceans that rely on sound to navigate, communicate, and hunt. At sufficient intensities, it can effectively mask the echolocation signals that whales and dolphins use to perceive their surroundings. Echolocation works by emitting high-frequency sounds and interpreting the echoes that return from nearby objects. When the acoustic environment is saturated with broadband noise, such as that generated by heavy rain, these echoes are buried under the environmental noise. The animal still emits its pulses, but the information that returns is compromised. It is a form of blindness, not visual but perceptual. Researchers funded by the European Union have been specifically studying the effect of rain noise on porpoises and dolphins, comparing it to the effect produced by motorized vessel traffic. The project, named RAIN, seeks to understand how these animals perceive and respond to natural noise sources compared to anthropogenic noise sources. A central hypothesis is that cetaceans, having evolved in naturally variable noise environments, may have developed adaptation mechanisms that help them deal with natural acoustic disturbances like rain in ways that the continuous noise of engines does not allow. Rain is intense but temporary, unpredictable but recognizable as part of the environment in which these animals have existed for millions of years. But rain also carries another acoustic layer that goes beyond the noise of the drops themselves. When it rains intensely enough, the runoff of fresh water on the surface creates a thin and less dense layer above the heavier saltwater below. This temporary stratification can alter how sound propagates, creating reflections and absorptions at frequencies that would normally cross the water column differently. The ocean is not just a homogeneous volume of water. It is a stratified environment with layers of different temperatures, salinities, and densities that behave like acoustic lenses and mirrors. Rain adds yet another layer to this already complex sonic architecture. Less than 0.001% of the total volume of the ocean has been seen by human eyes, even through cameras. Human exploration has a narrative of progress that we have become accustomed to receiving with satisfaction. Every peak climbed, every pole reached, every depth probed marks a point on a map that, we imagine, is becoming increasingly complete. Satellite images today cover every inch of the Earth's surface. High-resolution maps allow anyone anywhere in the world to explore city streets on other continents without leaving home. It seems reasonable to assume that the ocean, having been the object of fascination and scientific investigation for centuries, is reasonably well documented in some visual sense. This assumption is deeply wrong. Researchers from the Ocean Discovery League, a non-profit organization based in Rhode Island, published a study in the journal Science Advances in 2025 that gathered records from approximately 44,000 dives by submarines and remote vehicles conducted by 14 countries over more than 6 decades. The goal was to calculate how much of the deep seafloor had effectively been visually observed, whether by human eyes aboard submersibles or by cameras mounted on unmanned vehicles. The result was a fraction that is hard to write without needing to reread. Less than 0.001%. This means that 99.999% of the deep ocean floor has never been seen. It has never been photographed with high enough quality to be analyzed. It has never been observed in real time by any device whatsoever. The area that human beings have effectively seen is equivalent to a region roughly the size of the state of Rhode Island, one of the smallest states in the United States. The deep ocean, in turn, covers 2/3 of the planet's surface. To feel the weight of this number, it is useful to imagine the pace of progress needed to change this picture. Researchers estimated that even if 1,000 remote and manned submersibles went out every day and each covered about 3 square kilometers of the seafloor per day, it would take another 100,000 years to observe everything. 100,000 years. More time than Homo sapiens has existed as a species. The ocean is not just unexplored. It is unexplored on a scale that makes the word unexplored seem insufficient. And the data reveals an additional distortion beyond simple scarcity. More than 65% of all visual observations of the deep seafloor were made in waters near only 3 countries: the United States, New Zealand, and Japan. 5 countries together, which also include France and Germany, are responsible for 97% of all recorded visual observation dives. The rest of the ocean, including the vast stretches of the tropical Pacific, the South Atlantic, the Indian Ocean, and almost the entire floor of the polar zones, is an expanse almost completely invisible to the eyes of any human instrument. And observations made before 1980, which represent nearly 30% of the entire historical record, are mostly low-quality black and white images, with resolution and field of view insufficient for the detailed analysis that modern science requires. Some wineries age bottles at a depth of 60 meters, where constant pressure and temperature accelerate the aging process. The aging of wine is an art that deals, in its essence, with the control of conditions. The ideal temperature for aging a fine wine oscillates between 10 degrees Celsius and 14 degrees Celsius, and should vary as little as possible throughout the year. Light, especially ultraviolet light, degrades aromatic compounds and destabilizes color molecules. Vibration disturbs sediments and interferes with the slow chemical reactions that transform a young, harsh wine into something rounder and more complex. Throughout the centuries, humans have built underground cellars precisely to bring these conditions closer to the ideal. Cool, dark, quiet, stable. And then someone realized that there is an environment that does all of this naturally, with a precision that no man-made cellar can replicate, and that is available in abundance on almost every coast in the world. The seabed. The practice of aging wine submerged is not entirely new. Sunken champagne bottles were found in 19th century shipwrecks and recovered in surprisingly good condition, some of them still drinkable and of remarkable quality according to the tasters who tried them. But what began as an archaeological observation has become, in recent years, a deliberate practice. Wineries in Spain, France, Estonia, Bulgaria, and other countries have been experimenting with immersing bottles at depths ranging from 20 to 60 meters, monitoring what happens to the wine over months or years of immersion. The physics of the process is elegant. For every 10 meters of depth in seawater, the pressure increases by approximately 1 additional atmosphere. Atmospheric pressure at sea level is 1 bar. At a depth of 60 meters, the pressure is approximately 7 bars. For a bottle of sparkling wine, which internally contains a pressure of about 6 bars generated by dissolved carbon dioxide, this has an important consequence. At the point where the external pressure equals the internal pressure of the wine, the balance between the gases inside and outside the bottle stabilizes in a very different way than in a land-based cellar. Oxygen is effectively banned from the interior of the bottle because the external pressure prevents any gas exchange. And carbon dioxide, responsible for the bubbles and the structure of sparkling wine, cannot escape as easily. The result, according to producers and enologists who have studied the phenomenon, is an acceleration of autolytic reactions. The processes in which dead yeast cells inside the wine decompose and release compounds that give sparkling wine those characteristics of brioche, biscuit, and toasted nuts associated with great aged champagnes. The constant cold of the depths, which hovers between 4 degrees Celsius and 10 degrees Celsius depending on the location, slows down other processes that could introduce unwanted degradation. And the complete absence of light, combined with the absence of vibration caused by wind or human movement, creates an environment of stillness and stability that would be virtually impossible to reproduce artificially on land at the same cost. There is something bordering on paradox in wine aged at the bottom of the sea. Wine is, in its origin, a creature of the earth and the sun. It is born from the grape, which is born from the vine, which is born from the soil warmed by solar heat. All the language of wine is terrestrial. Terroir, minerality, the influence of limestone or granite on the compounds the vine absorbs. And then this product of the earth and the sun descends to the bottom of the ocean, to an environment where the sun never reaches, where the earth is a distant memory 2 or 3 kilometers above, and where life organizes itself according to rules completely different from those that shape the grape. And the ocean, with its pressure and its cold and its perfect darkness, does something to the wine that the earth does not. It transforms it in a different way. Not necessarily better or worse, specialists disagree on that, but clearly different. There are vineyards in Spain whose red wines spend months submerged at 60 meters in coastal inlets of the Basque Coast. There are champagne producers in France who have auctioned bottles aged under the Baltic Sea for considerable prices, attracting the attention of collectors who see the process not just as a curiosity, but as a source of wine with a story that no terrestrial cellar can offer. And there is a growing group of researchers studying the chemical composition of these wines before and after immersion, trying to identify precisely which compounds change, in what proportion, and at what depth the effects become most pronounced. Ancient maps suggest that we knew the outline of submerged coasts long before the invention of modern sonar. There is a category of historical discovery that does not fit easily into any narrative. It is not a relic that confirms what we already knew. It is not an anomaly that can be dismissed as a measurement error or creative fantasy. It is something that, the more it is examined, the more it insists on existing without there being a completely satisfactory explanation. The Piri Reis map belongs to this category, and once you know its story, it is hard to stop thinking about it. In October 1929, a German theologian named Gustav Adolf Deissmann was working on cataloging forgotten documents at the Topkapi Palace in Istanbul when he found a map fragment drawn on gazelle skin. The map was folded and tucked away, without any inventory describing it adequately. It was just one object among others, forgotten for decades. When it was opened and studied, it was revealed to be signed by Hagji Ahmed Muhyiddin Piri, known as Piri Reis, an admiral of the Ottoman Navy, experienced navigator and cartographer. The date inscribed on the map, 1513, and what the map showed caused a stir that has not ended to this day. The map represented the Atlantic with reasonable precision for the standards of the time. The western coast of Africa was recognizably outlined, the east coast of South America as well. Piri Reis indicated in notes that he had compiled the map from approximately 20 sources, including 8 Ptolemaic maps, 4 Portuguese maps, 1 Arabic map, and 1 map attributed to Christopher Columbus, a collection of documents from diverse eras and origins that he synthesized into a single cartographic work. But what caught the immediate attention of any observer who knew the planet was not South America. It was what lay at the far southern end of the map. At the lower limit of the composition, separated from the southern tip of South America by a channel, there was an outline of land that continued eastward and described an irregular coast, entering inlets and advancing into capes with details that seemed too specific to be fantasy or invention. And when 20th century researchers superimposed this outline onto a modern map of Antarctica, the correspondence was disturbing. Antarctica was not discovered as a continent until 1820. It was not explored in detail until the 20th century, and the actual shape of its coastline, under the ice, only became known with precision after seismic techniques were used to map the relief hidden by kilometers of ice covering the continent. Even so, the comparison with the outline of the Piri Reis map revealed a resemblance that the U.S. Hydrographic Office, consulted in 1960 by Professor Charles Hapgood of Keene College, described in official correspondence as remarkably consistent with the results of the seismic profile obtained in Antarctica, indicating that the coast had been mapped before being covered by the ice cap. Hapgood deepened the investigation in his book Maps of the Ancient Sea Kings, published in 1966, arguing that the Piri Reis map, along with other medieval maps that also seemed to contain geographical information of inexplicable precision, could indicate the existence of a cartographic tradition much older than known civilizations, a tradition that would have reached medieval compilers through chains of copies whose origins were lost. The hypothesis gained an unlikely supporter, Albert Einstein, who read Hapgood's manuscript before its publication and wrote in correspondence that the theory deserved serious consideration and could have significant implications for the history of civilization. The majority position among historians and cartographers is more cautious. They argue that the supposed outline of Antarctica may be a deformed representation of the southern tip of South America, stretched eastward by projection errors accumulated over countless copies. That the similarities with the Antarctic coast may be coincidences amplified by selective comparisons. That the general precision of the map contains errors significant enough to suggest that its most exact parts were the product of good luck as often as genuine knowledge. These are reasonable objections. And yet the map exists, with its outline in the south, with its date of 1513, with its note of lost sources that no one can name for certain, with the correspondence of a United States military official saying he has no idea how the data on this map can be reconciled with the supposed state of geographical knowledge in that year. The emperor penguin can dive deeper than 500 meters to hunt. The emperor penguin is the largest living penguin, can reach 1.2 meters in height and weigh up to 45 kilograms. It does not fly. It never learned to fly, or more precisely, the ancestors of the species that gave rise to penguins abandoned flight tens of millions of years ago in exchange for a completely different mastery. Instead of cutting through the air, emperor penguins cut through the water with extraordinary efficiency, using their wings transformed into rigid flippers to propel themselves at speeds that can reach 30 kilometers per hour during short bursts of pursuit. But speed is not what makes these animals truly remarkable as divers. It is depth. The deepest dive recorded for any penguin was that of an emperor penguin that descended 564 meters below the surface, more than half a kilometer deep. It is the deepest dive ever documented for any bird anywhere in the world. The animal that performed it did so on a single breath, a single inhalation of air on the cold surface of the Southern Ocean, and then a descent into an environment of increasing darkness and increasing pressure where most air-breathing animals could not survive for more than a few seconds. To understand what this dive requires physically, it is useful to think about what depth does to a body. For every 10 meters of depth, pressure increases by 1 atmosphere. At 564 meters, the pressure is more than 56 times the pressure at sea level. For a human being without equipment, this would be almost instantly fatal. Lungs would be compressed to a fraction of their normal size. Nitrogen dissolved in the blood would cause narcosis and eventually toxicity. The pressure alone would cause the collapse of tissues and cavities. For an emperor penguin, these same physical factors exist, but evolution has equipped them with adaptations that transform extreme diving not into a limit to be heroically surpassed, but simply into normal foraging behavior. Before diving, the emperor penguin partially exhales the air from its lungs instead of inhaling to the maximum, which reduces the amount of compressible air in its body and minimizes the risks associated with compression at depth. Its spleen is exceptionally large relative to its body size and functions as a reservoir of oxygen-rich red blood cells, which are released into the bloodstream during the dive to extend oxygen transport capacity. The concentration of myoglobin, the protein that stores oxygen in the muscles, is much higher in penguins than in typical birds, making the emperor penguin's muscle appear almost dark brown instead of the light red we would expect. Its heart rate slows dramatically during immersion, a response called diving bradycardia, which reduces oxygen consumption by the heart and allows the available supply to be prioritized for the brain. Most dives of an emperor penguin in normal feeding activity go between 100 and 200 meters. This is already an impressive depth for any air-breathing animal. The deepest dives, like that 564-meter record, are exceptional even within the species. The duration can exceed 20 minutes in a single dive, and a penguin in active search of food can perform dozens of successive dives throughout a single day. The primary prey are fish and squid that inhabit the ocean's twilight zone, the layer where sunlight barely penetrates, where the temperature is a few degrees above zero, and where life exists according to rules dictated by darkness and cold. In Antarctica, fingers of saline ice called Brinicles descend to the bottom and freeze everything they touch instantly. Ocean water does not freeze like the freshwater of a lake. When a lake in winter covers itself in ice, the process is relatively simple. The water cools, reaches 0 degrees Celsius, and solidifies. The salt in the ocean complicates all of this. Salt molecules interfere with the formation of ice crystals, requiring lower temperatures for solidification to occur. Sea ice freezes at approximately -1.8 degrees Celsius. But when sea ice forms, it does not incorporate salt uniformly. The ice crystals that build up are relatively pure. The salt is progressively excluded from the solidification process and concentrates in the water that still remains liquid within and around the forming ice. The result is the creation of brine channels, small filaments and pockets of extremely salty water trapped within a porous ice structure. This brine is denser and colder than the surrounding seawater, with temperatures that can reach -15 degrees Celsius compared to the -1 degree Celsius to 4 degrees Celsius of the surrounding oceanic water. And it is heavier. When conditions are right, when the surface ice cracks or when the pressure of the ice pushes the brine out of the internal channels, this extremely cold and dense water begins to leak into the ocean below. And when it leaks, it descends. And as it descends, what it encounters freezes. The phenomenon has a name, Brinicle, a term created from brine, combined with icicle, those fingers of ice that form on the roofs of houses in winter. A brinicle is an underwater ice finger that grows downward, but where a roof icicle is static, a brinicle is actively growing and actively killing. As the brine descends, it encounters the fresher water around it. This water, which is not salty enough to remain liquid at the temperature of the descending brine, freezes on contact. A tube of ice forms around the descending column of brine, a shell that grows centimeter by centimeter, meter by meter, toward the bottom. Brinicles can grow at rates of several meters per hour in favorable conditions. In real time, the process looks slow. In time-lapse, like the footage shot by the BBC for the program Frozen Planet in 2011, it looks like an onslaught. A finger of ice extending downward in continuous motion, and around it, a freezing that propagates like a veil being closed over the seabed. When the Brinicle finally touches the bottom, it does not stop. The brine continues to flow through the hollow tube and spreads over the substrate, and what had been living seabed, with urchins, starfish, small worms, and crustaceans, is enveloped by the ice that forms on contact. The animals cannot escape in time. They get stuck exactly where they were, instantly immobile, encased in a cocoon of ice that grew over them in a matter of minutes. The BBC called the phenomenon the finger of death, and the footage became one of the most shared images of marine physical behavior in recent years. But Brinicles are not creatures. They have no intention. They do not hunt. They are simply the result of temperature and density gradients doing what temperature and density gradients always do, balancing themselves. The brine descends because it is heavier. The ice forms because the temperature is too low for the water to remain liquid. The bottom freezes because it was in the way. It is physics, pure and without ornament. What makes the process disturbing for those who watch it is not cruelty. It is precisely the absence of it. An ice structure that grows, that kills, that expands, that simply happens without any agency involved other than the laws governing temperature and pressure. 99% of global internet data travels through cables on the seabed, not through satellites. There is an infrastructure that sustains almost all of the planet's digital communication and that the vast majority of people do not know exists. Not because it is secret, but because it is in a place we never see, in an environment that remains invisible to everyday life. It is at the bottom of the sea, and it is responsible for carrying practically the entire flow of data that constitutes the global internet. Messages, transactions, videos, voice calls, financial operations, scientific data. Everything that crosses borders between countries and continents, in the overwhelming majority of cases, travels through fiber optics submerged in the ocean. Satellites dominate the imagination when thinking about global communication. They are above our heads, visible as points of light crossing the night sky, and they seem like the most obvious way to send a signal from one side of the planet to the other. But satellites have fundamental physical limitations that make them inadequate for the raw volume of modern data traffic. A satellite in geostationary orbit is at an altitude of about 36,000 kilometers, which introduces a latency of at least 600 milliseconds for a signal round trip, enough time to significantly degrade voice calls and real-time communications. Low-orbit satellites have lower latency but much more limited data capacity and require immense constellations to provide continuous coverage. Submarine fiber optic cables transmit data at the speed of light through glass, with latency measured in tens of milliseconds for intercontinental routes, and a bandwidth capacity that has increased exponentially with advances in optical multiplexing. There are currently more than 600 active submarine cables, totaling more than 1.3 million kilometers of cumulative length, carrying data that sustains more than $3.65 quadrillion in annual digital transactions. Each cable is a remarkably slender structure for what it carries, with the approximate thickness of a garden hose over most of its length. Inside, glass fibers the diameter of a human hair. Outside, several layers of protection that vary depending on the depth. In shallow waters near the coast, where anchors and fishing nets represent a real risk, the cables are buried in the seabed and coated with multiple layers of steel and resistant plastic. In deep waters, where mechanical risk is lower but pressure is enormous, the coating is lighter. In the abyss, the crushing pressure compresses the protective layers around the fibers firmly enough to maintain integrity. But the cable itself becomes surprisingly simple in its structure. Companies like Google, Meta, Microsoft, and Amazon have begun to build and operate their own submarine cables instead of relying exclusively on traditional telecommunications operators. Investment in submarine cables between 2025 and 2027 is projected to exceed $13 billion, almost double the immediately preceding period. The demand for bandwidth is the engine of this growth. Large cloud service providers need intercontinental capacity that grows by tens of % per year, and the only way to deliver that capacity is to place more fibers on the seabed. The points of vulnerability of this system are at the ends, where the cables emerge from the ocean and touch land, and in shallow waters where physical risks are greater. Undersea earthquakes, sediment movement, and volcanic activity occasionally damage cables in deep zones. In 2006, an earthquake in Taiwan damaged several cables in the South Pacific, causing significant degradation of communications across Asia for days. Repairing a cable on the ocean floor requires specialized ships, deep immersion equipment, and weeks of careful work. Managers of this infrastructure, such as the person responsible for Google's submarine cable projects, have described the work as managing a multidimensional and extremely complex chessboard. You're absolutely right to call me out on that. I missed the final 3 sections of your last text. I'll fix that immediately and provide the complete translation for that entire block, from the TMAO molecules to the Starfish, exactly as you requested, no removals, no latex, and H2 for the titles. At extreme pressures, proteins in common cells would collapse without a molecule called TMAO, which stabilizes them. Life in the oceanic abyss is not just resilient in the popular and imprecise sense we use to praise things that survive difficult circumstances. It is resilient in the most literal molecular sense possible. The proteins inside the cells of deep-sea animals are being actively protected against collapse by a chemical substance that rises in concentration proportionally to the depth at which the animal lives. This substance has a name that, by a pleasant coincidence, matches what it does for the organism: trimethylamine N-oxide, or TMAO. To understand what TMAO does, it is necessary to understand what pressure does to proteins. Proteins are functional molecules that only work because they have a specific shape. This shape, called the native conformation, is maintained by a delicate balance of forces: hydrogen bonds, hydrophobic interactions, and electrostatic attractions between different parts of the amino acid chain that folds upon itself in a precise 3-dimensional structure. The enzyme that digests a food, the receptor that captures a neurotransmitter, the channel that controls the flow of ions across a cell membrane, all depend on their shape to perform their function. An unfolded protein is, in most cases, a useless or actively harmful protein. The pressure of the deep ocean acts on proteins in a way that high temperature also does, but through a different mechanism. It forces water molecules into the internal spaces of the folded protein, destabilizing the interactions that maintain its shape. As pressure increases, the thermodynamic equilibrium between the folded and unfolded conformation shifts progressively in favor of unfolding. For a shallow water fish protein, pressures at 500 or 1,000 meters of depth would equal unfolding and functional loss. The enzyme lactate dehydrogenase, for example, which participates in cellular energy metabolism and exists in practically all vertebrates, has its activity significantly compromised by pressures that correspond to a few hundred meters of depth when tested in vitro without protection. TMAO solves this problem elegantly. Shallow water fish have TMAO concentrations in the muscle that rarely exceed 70 millimoles per kilogram. Bathyal fish, which inhabit the zone between 200 and 4,000 meters, have higher concentrations. Abyssal fish in the deepest zones have concentrations that can reach 288 millimoles per kilogram or more. And when researchers measured this relationship carefully, they discovered that it is almost linear. The deeper the animal lives, the more TMAO its cells contain, in a proportion that remarkably corresponds to the amount of TMAO needed to compensate for the destabilizing effects of pressure at that specific depth. The mechanism by which TMAO protects proteins operates at 2 simultaneous levels. First, it alters the structure of the water around it, making it difficult for water molecules to penetrate the internal spaces of the protein that pressure would try to open. The TMAO molecule has a strong affinity for hydrogen bonds with water and retains water molecules around it so efficiently that it reduces the amount of free water available to invade the protein. Second, it acts as a molecular confinement agent, a nanoscopic crowder that increases the stability of the folded conformation by the simple effect of occupying space and making the unfolded state energetically less favorable because it would require more volume. It is a double solution to a single problem: maintaining the shape of proteins in an environment that would insist on unfolding them. TMAO is also the reason why deep-sea fish have that strong and pungent smell that anyone who has ever opened a package of salted cod or dried fish knows. TMAO itself is odorless, but when the fish dies and bacteria begin to decompose it, bacterial enzymes convert TMAO into trimethylamine, TMA, which is the compound responsible for the characteristic fishy odor. The more TMAO in the muscle of the animal in life, the more TMA available in the decomposition, and the more intense the odor. The smell of fish, in short, is the trail left by a molecular protection system that allowed life to inhabit the most inaccessible depths of the planet. Moonlight penetrates only to about 50 to 100 meters in the water. The moon is the brightest object in the night sky. On a night of full moon and clear sky, it illuminates the world enough to cast sharp shadows and for humans with good vision to walk without artificial aid. This light has quality and history. It is sunlight reflected by the lunar surface and returned to the planet with the same spectral composition, the same spectrum of wavelengths as the original sunlight. The only difference is intensity. And this difference in intensity is what determines everything about how moonlight behaves within the ocean. The surface of the moon reflects approximately 12% of the sunlight it receives, a reasonably dark surface in comparative terms. The result is that the intensity of full moon light on the Earth's surface is approximately 1 million times less than that of direct sun at noon. 1 million times. This is a number that seems abstract until you think about the physical consequences. Sunlight penetrates the ocean in sufficient quantities to sustain photosynthesis until approximately 200 meters of depth. Moonlight begins with a millionth of the solar intensity. This means its effective penetration depth is radically different. The physics of light attenuation in water operates logarithmically. At each meter of depth, a constant fraction of the remaining light is absorbed and scattered. In very clear oceanic water, about 2.3% of light intensity is lost per meter of depth. For sunlight, this means that detectable traces reach a few hundred meters. For moonlight, with its initial intensity a million times lower, the calculation leads the detectable signal to extinguish much sooner. At about 50 to 100 meters of depth, depending on the clarity and conditions of the water, moonlight becomes imperceptible even for sensitive instruments. Below that, the night does not exist in the same way we know it on land. There is simply no luminous distinction between a full moon night and a new moon night. The ocean below 100 meters lives in perpetual darkness, independent of any astronomical event on the surface. But this penetration limit, modest in comparison with sunlight, has a surprising importance for life in the shallow twilight zone of the ocean. Many marine organisms perform daily vertical migrations, rising towards the surface at night to feed on the abundant plankton in the upper layers illuminated during the day, and descending to the depths during the hours of light to escape predators that hunt visually. This movement is guided by luminosity. Darkness signals relative safety, and the animals rise. Clarity signals danger, and they descend. Moonlight interferes with this system in a documented way. On full moon nights, the organisms that would normally make this vertical migration may reduce their ascent or remain deeper, as the lunar illumination on the surface and in the upper layers of the ocean is sufficient for visual predators to operate with reduced but real effectiveness. This has cascading effects through the food chain. The zooplankton that remains deeper is less available to the fish that depend on it, which in turn are less available to larger predators. The phase of the moon, therefore, is not just an aesthetic or astronomical phenomenon for the ocean. It is an environmental signal that regulates behaviors, distributions, and interactions in layers of the water column that most people would never imagine are affected by the presence or absence of lunar light. The ocean floor at Point Nemo houses more than 260 discarded spacecraft and stations. We have already encountered Point Nemo on this journey. We return to it now for a different reason, not to contemplate its geographical isolation, but to examine what human beings have chosen to do with it. Because the most remote point of the ocean, this place so far from any coast that astronauts in orbit are its closest neighbors, has become in recent decades something that Jules Verne could hardly have imagined when naming the location after his fictional sailor, the largest spacecraft cemetery in the world. Between 1971 and 2018, the planet's main space powers deposited more than 263 space objects in the ocean around Point Nemo. The first was in 1971, when the Soviet Union deorbited a Salyut series space station. Since then, the list has grown to include more than 140 Russian Progress series resupply ships, 6 Salyut series stations, 6 Japanese cargo transfer vehicles, 5 European Space Agency cargo ships, SpaceX rocket fragments, and the most notable item of all, the Soviet space station Mir, which operated from 1986 to 2001 and was deorbited in a controlled manner so its debris would fall precisely in this region of the South Pacific in March of that year. The process by which a spacecraft ends up at Point Nemo is calculated with precision. When a station or space vehicle approaches the end of its useful life, mission operators execute controlled maneuvers that progressively reduce its orbit. Upon re-entry into the atmosphere, friction with the upper layers of air heats the object to temperatures that ignite and sublimate most of its components. Aluminum, titanium, polymers, most of the electronics. All of this turns into plasma and disperses. But some components, manufactured with materials of a very high melting point such as certain stainless steel alloys, pressure fuel tanks, and containment module shields, survive re-entry in fragments that vary from pieces the size of a hand to structures as large as a small car. It is these fragments that must fall somewhere, and Point Nemo is the safest place there is. The choice is not just about isolation. It is also about orbital trajectory. Satellites and stations in equatorial orbits or near it naturally cross over the South Pacific at certain moments of their orbits. With proper calculations of remaining propulsion and re-entry timing, mission controllers can direct the debris to a relatively precise impact window around the Point Nemo coordinates. It is not a perfect science, and there is a margin of error of dozens of kilometers, but compared to any inhabited coast, this margin is irrelevant. Point Nemo has already received the past of space exploration. It is scheduled to receive its most significant present in 2031, when the International Space Station, the largest structure ever built by humans in space, with its 400 tons and its modules inhabited continuously since November 2000, is deorbited at the end of its operational life. NASA has already issued a request for proposal for the vehicle responsible for executing the final maneuver. When the ISS descends, most of it will transform into plasma over the Pacific. What remains will fall at Point Nemo, in the depths of approximately 4,000 meters of cold and dark ocean that already guard the debris of decades of human presence in space. A shrimp's heart is located inside its head. The human body obeys a plan of internal organization that we learn so early it seems universal to us. The heart is in the chest. The brain is in the head. The liver is in the abdomen. These locations are not arbitrary. They follow an evolutionary and developmental logic that the vertebrate branch has preserved with remarkable consistency over hundreds of millions of years. This is why a doctor who knows human anatomy can recognize the corresponding organs in a fish, an amphibian, or a reptile. The blueprint is the same. Proportions change, shapes change, but the heart is in the thoracic region, protected by the bony cage, centered in the chest. The shrimp did not read this manual. And not because it is a simpler or more primitive animal. It is because it belongs to a branch of animal life that arrived at the problem of how to organize a body in a radically different way, and that found solutions that work perfectly well within its own logic. The shrimp's heart is in the head. More precisely, it is in a structure called the cephalothorax, which is the fused anterior region that combines what, in other animals, would be the separate head and thorax. In the shrimp, these two regions form a single compact segment covered by a protective carapace. And inside this compartment, all the vital organs are grouped together. Eyes, primitive brain, anterior digestive system, gonads, and the heart, which rests in the upper dorsal part of the cephalothorax, just behind the cephalic region itself and directly under the carapace. The evolutionary reason for this configuration begins with the body plan of arthropods, the group that includes shrimps, crabs, lobsters, insects, and spiders. Arthropods developed exoskeletons, rigid external armor instead of the internal skeletons of vertebrates. An exoskeleton offers excellent protection, but imposes a different logic on how internal organs can be distributed. Since there is no internal ribcage to protect the heart specifically, it makes sense for the heart to be in the region that has the most robust external protection, which in the shrimp is precisely the cephalothorax with its thick carapace. The shrimp also has a circulatory system fundamentally different from ours. It is an open system, which means there are no veins and arteries confining the blood in closed tubes. The heart pumps hemolymph, the circulatory fluid of arthropods that plays the role of blood, out through openings called ostia to cavities called hemicoelic sinuses. The hemolymph bathes the organs directly, without the mediation of capillaries, delivering oxygen and nutrients by direct contact with the tissues. Afterwards, it drains back to regions from where it is aspirated again by the heart. It is a circulation system that works more like an internal tide than like the pump and piping of the vertebrate cardiovascular system. Shrimp hemolymph is not red. It is blue-green, a consequence of containing hemocyanin instead of hemoglobin as an oxygen carrier protein. Hemoglobin uses iron in its active center, which is what makes it red. Hemocyanin uses copper, and copper, when oxygenated, gives the fluid a blue hue. It is the same reason why some spiders and octopuses also have blue blood. Copper, as the central element of the oxygen carrier protein, is one of the alternative solutions that evolution found for the same problem of transporting respiratory gas in body fluids. Starfish put their stomach outside their body to digest prey inside their own shells. In biology, there is a principle that medical students learn early. The interior and exterior of the body are distinct and rigidly separated categories. What is inside the organism is protected, regulated, and maintained in precise homeostatic conditions. What is outside is the environment, unpredictable, hostile, full of pathogens and conditions that the organism works actively to keep at a distance. The intestinal wall, for example, is one of the most strongly regulated borders in the entire human body, with multiple layers of protection and immunity to ensure that what is outside the intestinal tissue does not cross indiscriminately inside. Digestion occurs inside a tube that, despite being physically inside the body, is biologically separated from the cellular interior by these barriers. The starfish simply does not work like that. It has put its stomach outside. The process is technically called gastric aversion, and it is one of the most cinematically extraordinary behaviors that exists among marine invertebrates. When a starfish finds a prey that it cannot swallow whole, be it a mussel, an oyster, a sea urchin, anything protected by a shell or casing that the starfish's oral opening would not accommodate, it solves the problem by completely eliminating the intermediate stage of ingestion. It inserts or projects its stomach out of its body, directly into the interior of the prey, and digests the animal inside its own shell. The mechanism begins when the star identifies and positions itself over the prey. Its hundreds of tube feet, the hydraulic muscular tubes that cover the lower face of each arm, apply suction on the shell's surface. The force applied by all these feet together can sustain continuous traction for hours if necessary, and eventually overcomes the resistance of the adductor muscles that keep the oyster or mussel valves closed. The opening does not need to be large. A 1 millimeter gap is enough. Through the minimal fissure that opens between the valves, the star everts its cardiac stomach, one of its two stomachs, pushing it out through the mouth and introducing it into the space between the valves. The stomach, now on the outside, envelopes the soft tissues of the prey and begins to secrete digestive enzymes directly over them. Digestion occurs externally, inside the victim's own shell. The proteins and fats of the animal's tissues are broken down by these enzymes into a semi-liquid mixture that the star then sucks back into the body along with the inverted stomach. What remains when digestion is complete is the empty shell. Clean. The only trace of the meal is the exoskeleton the prey used as a defense, now emptied of everything that was inside. Researchers at Queen Mary University of London discovered that the hormone oxytocin, the same substance associated with social bond formation and the feeling of love in mammals, is the chemical signal that triggers gastric aversion behavior in starfish. When researchers injected oxytocin into starfish that were not feeding, the stars began to perform the complete aversion behavior, including the arched posture and the projection of the stomach, even without any prey present. It was called sham feeding, the behavior of digesting externally with nothing to digest. That the same chemical compound that makes us feel close to the people we love is the signal that tells a starfish to expel its stomach is one of the most disconcerting coincidences of comparative biology. The narwhal's horn is a tooth with 10 million nerve endings used to sense water chemistry. The narwhal is an Arctic cetacean, a close relative of the beluga, which can reach 5 meters in length and inhabits the icy waters around the Canadian Arctic, Greenland, and parts of northern Russia and Norway. For centuries, it was the most important animal for one of the largest commercial frauds in European history. Its tooth, spiral, long and capable of exceeding 3 meters in adult males, was sold as unicorn horn during the Middle Ages and the Renaissance at prices that reached several times its equivalent weight in gold. Kings and queens bought fragments as amulets and antidotes against poison. Royal scepters were built with them. The coronation throne of Denmark was made entirely of narwhal tusks in the belief that the material was unicorn horn, endowed with magical and medicinal properties. The secret of the material's origin was protected by merchants for centuries because revealing that it came from a real creature, and not a mythical being, would destroy its value. But what this tooth really is and what it actually does is more interesting than any myth. The narwhal's horn is a tooth. Specifically, it is the upper left canine, which in adult males grows outward in a left-handed spiral and can reach between 2 and 3 meters in length. In females, this tooth rarely grows beyond a small rudiment hidden by the lip. Occasionally, males develop 2 teeth, creating the bidentate configuration that appears in some historical photographs. The tooth grows in a spiral along its entire length, always in the same direction, and no current theory completely explains why the spiral goes in one specific direction instead of another. For decades, the purpose of the narwhal's tooth was one of the most debated mysteries in marine biology. Theories proposed over time included its use as a defensive weapon against predators, as a tool for breaking ice, as an instrument for capturing prey, as a sexual signal analogous to the peacock's tail, and as an organ for detecting pressure changes in the water column. None of these hypotheses were completely satisfactory, and some were contradicted by behavioral observations. Then, in the early 2000s, dentist and researcher Martin Weah initiated a program of anatomical and functional study of the narwhal tooth that would change the conversation. What Weah and his team discovered by examining cross-sections of the tooth with high-resolution microscopy was that the internal structure is radically different from what would be expected from a conventional tooth. The outer surface of the narwhal tooth is not covered by the hard enamel that protects the teeth of most mammals. Instead, it is perforated by millions of tiny channels, pores that allow seawater to penetrate directly into the interior of the tooth. These channels connect to dentin tubes that lead to the center of the tooth, where there is a pulp rich in nerves and blood vessels that extend directly to the brain. The result is a sensory organ of impressive nerve density. With approximately 10 million nerve endings distributed along its length, the narwhal tooth is capable of detecting variations in the chemical composition of the water around it with a sensitivity that comparable scientific instruments would take decades to achieve. Weah demonstrated this experimentally by exposing narwhals to solutions of different salinities while monitoring their heart rate. When the salinity around the tooth increased, suggesting that the water was freezing and potentially trapping the animal, the narwhal's heart rate increased measurably. When exposed to fresh water, it decreased. The tooth felt it, and the body responded. It is possible that the narwhal tooth senses more than just salinity. Temperature, partial pressure of dissolved gases, perhaps the presence of chemicals released by prey or predators. The structure allows all of this in principle, and nature rarely builds sensory organs of such high density for a single use. The narwhal uses something that for millennia seemed to humans like an extravagant decoration, an evolutionary exuberance comparable to the unicorn horn of dreams, for a function that most animals do not have. Sensing the chemistry of the ocean directly, in real time, through the tongue of the sea that enters through the pores of a tooth and speaks to the animal's nerves in a language that no other sense could translate. Dolphins have been observed using pufferfish to release small doses of toxins and enter a trance-like state. There is a set of animal behaviors that researchers describe with extreme scientific caution because the implications are difficult to reconcile with the more comfortable ideas we have about what separates human beings from other animals. The deliberate search for altered states of consciousness through the consumption of psychoactive substances used to be listed as one of those exclusively human behaviors. Then came studies of monkeys that ferment and consume fruit to get intoxicated. Then birds that eat hallucinogenic plants. And then, in 2013, a BBC production documented in images what biologists and field observers had speculated for years. Young dolphins deliberately manipulating pufferfish to obtain controlled doses of a potentially psychoactive neurotoxin. The pufferfish, when disturbed, releases tetrodotoxin as a defense mechanism. Tetrodotoxin is one of the most potent poisons known in nature, blocking sodium channels in nerve and muscle membranes and causing progressive paralysis. In high doses, it is lethal to practically any vertebrate. In much smaller doses, the effects on the nervous system are milder and can include effects similar to painkillers or mild sedatives. It is this gradient between the dose that kills and the dose that produces something different and non-fatal that dolphins have apparently learned to explore. The BBC footage showed groups of young dolphins passing a pufferfish among themselves with behavior that producers and field biologists described as careful and deliberate. Instead of biting hard or consuming the fish, the dolphins nibbled it lightly, enough to stimulate the release of small amounts of toxin, and then passed the fish to the next animal. After this interaction, the group's behavior changed. The dolphins floated near the surface, moving slowly, with the relaxed posture and half-closed eyes that observers described as a trance. They remained in this state for a few minutes, after which their usual active behavior resumed. Zoologist and producer Rob Pili, who worked on the filming, described the episode to the Sunday Times as a case of young dolphins intentionally experimenting with something we know to be intoxicating. Proper scientific caution requires recognizing what we do not know for sure. We cannot confirm the dolphins' subjective experience during these moments, we cannot measure toxin concentrations in their systems, and the interpretation of the behavior as a search for a trance may be projecting human categories onto what could be, in principle, a behavior of another type. This caution is reasonable and necessary, but the behavior itself is documented, and it does not exist in isolation. Dolphins are among the few animals for which there is substantial evidence of cultural behavior transmitted socially between generations, behaviors learned from other individuals that are not genetically determined but culturally propagated. The technique of using sponges on the snout to protect the beak while scavenging the bottom for prey, observed in specific populations of dolphins in Australia and transmitted from mothers to offspring, is a well-documented example. If the behavior with the pufferfish is culturally transmitted, if young dolphins learn from adults or peers that this specific fish treated in this specific way produces this specific effect, then we are facing something that scientific language describes with difficulty and that everyday language describes with ease: pharmacological knowledge culturally transmitted between non-human animals. Seahorses are the only animals where the male carries the eggs and gives birth. Reproduction is, in almost the entire tree of animal life, a story of asymmetry. The female carries. The male fertilizes and often moves away. This distribution of roles is so ubiquitous among vertebrates that we tend to treat it as a biological fact equivalent to a physical law, something inevitable, determined by the simple fact that eggs are larger and more metabolically costly than sperm. The female who produced the egg has more initial investment and, therefore, more reason to continue investing during gestation. It is a logic that explains reproductive patterns in fish, amphibians, reptiles, birds, and mammals with remarkable consistency. The seahorse found an exception, and not just a superficial exception where the male cares for the eggs externally. A deep exception, where the male becomes pregnant, nourishes the embryos within an anatomical structure comparable to the uterus, and gives birth to live young. The seahorse belongs to the genus Hippocampus and the family Syngnathidae, which also includes pipefish and sea dragons. All members of this family exhibit some degree of male parental care, but seahorses have taken this investment to its most complete form. The male has a brood pouch located in the anterior part of the trunk, in the ventral region, immediately below the point where the trunk curves toward the tail. This pouch is the centerpiece of the species' entire reproductive process. The seahorse mating ritual begins days before the egg transfer and involves a dance that researchers describe as one of the most elaborate courtship behaviors observed in fish. The couple spends hours swimming side by side, synchronizing movements, intertwining tails, and changing color in response to each other. This dance serves a practical function beyond the choreographic aspect. It synchronizes the physiological conditions of both partners so that the transfer occurs at the exact moment when the male's pouch is prepared to receive the eggs. When synchrony is established, the female inserts a tube called an ovipositor directly into the opening of the male's pouch and deposits her eggs. The male fertilizes them internally with his own sperm inside the pouch, and the mating is complete. What happens next is biologically extraordinary. The male's pouch is not simply a passive container. It is an active organ with vasculature, tissue similar to the placental, and the ability to actively regulate the environment around the embryos. The male provides oxygen and nutrients through this network of blood vessels, in a manner analogous to what the placenta does in mammals. He also regulates salinity within the pouch throughout gestation, increasing it progressively as the embryos develop, acclimating the young to the saline conditions of the ocean before they are released. Gestation lasts between 14 and 28 days depending on the species and water temperature. The birth of the male seahorse involves muscle contractions and postural behaviors that researchers from the University of Sydney documented in 2022 with details that revealed significant differences compared to female birth in other vertebrates. Instead of relying primarily on smooth muscle contractions as occurs in the mammalian uterus, the male seahorse seems to use striated muscle contractions of the trunk combined with body-bending movements to expel the young through the pouch opening. The young emerge in groups, sometimes in hundreds or even 1,000 at once, depending on the species. Each offspring is already a miniature seahorse, with all the adult structures formed, capable of swimming and feeding independently from the first moment of life. The survival rate in the days following birth is, however, brutal. The vast majority of offspring do not survive the first weeks, consumed by predators or lost in currents before finding a substrate to anchor themselves. The most difficult evolutionary question is not how male pregnancy works in seahorses. It is why it arose. The most accepted hypothesis is that transferring eggs to the male's pouch frees the female to produce a new clutch of eggs while the male is still pregnant, increasing the couple's total reproductive rate. But why the male, and not the female, ended up with the role of gestating remains an open question. And the fact that the same hormone, oxytocin, which triggers labor in mammals, plays a role in triggering birth behaviors in the male seahorse suggests that some evolutionary solutions to the problem of releasing young into the world were discovered more than once, in branches of life that diverged hundreds of millions of years ago, as if the universe had preferences about how certain things should work. Horseshoe crab blood is blue and used to ensure that all human vaccines are safe. The horseshoe crab is not a crab. The resemblance to crustaceans is superficial, a product of forms that converge under similar ecological pressures. Anatomically, the horseshoe crab is closer to spiders and scorpions, belonging to the group of chelicerates, and its lineage in the fossil record dates back approximately 450 million years, making it one of the animals with the longest continuous presence on the planet. The horseshoe crab survived the Permian extinction, which wiped out more than 90% of marine species. It survived the Cretaceous extinction, which ended the dinosaurs. And while it survived, it silently developed something that no other creature on the planet has in the same way. An immune system so primitive and so effective that it became, 500 million years after its origin, the indispensable guardian of the human species' medical safety. The blood of the horseshoe crab is blue. The reason, as in shrimp, is hemocyanin with copper instead of hemoglobin with iron. But color is only the most visually obvious feature. What makes this animal's blood irreplaceable for modern medicine are its amoebocytes, the immune cells that circulate in this metallic blue fluid. These cells developed over hundreds of millions of years an extremely refined defense mechanism against one of the greatest risks primitive organisms faced: bacterial endotoxins. Endotoxins are fragments of the cell walls of certain bacteria that, when released in sufficient quantities into an animal's blood, trigger devastating immune responses, high fever, septic shock, and death. For an animal without an adaptive immune system like the horseshoe crab, a fast and effective defense against endotoxins was a matter of survival. The solution that evolution developed was an ultra-fast clotting mechanism. When horseshoe crab amoebocytes come into contact with bacterial endotoxins, they gel and form an almost instantaneous clot around the invading substance, immobilizing it before it can propagate. In the 1950s and 1960s, researchers Frederick Bang and Jack Levin, working at the Marine Biological Laboratory in Woods Hole, Massachusetts, observed that horseshoe crab blood clotted rapidly when exposed to bacterial extracts. Understanding the implication, they developed a test based on this property: limulus amoebocyte lysate, or LAL, a preparation made from the crab's amoebocytes that reacts detectably in the presence of endotoxins at extremely low concentrations. The LAL test can detect bacterial contamination at levels of parts per trillion, making it orders of magnitude more sensitive than previous tests based on injection into live animals. Since the 1970s, when the LAL test was adopted as a standard by the US FDA and regulatory agencies around the world, it has been required to verify the safety of virtually every medical product that enters the human body. Vaccines, injectable drugs, intravenous fluids, cardiac stents, catheters, pacemakers, orthopedic implants. All of these are tested with LAL before being approved for use. If you have ever received a vaccine, a hospital injection, or undergone a surgical procedure with an implant, in all probability the product that entered your body was validated using the blue blood of a horseshoe crab. The process of obtaining this blood involves the capture of live horseshoe crabs during their coastal breeding migrations. They are transported to pharmaceutical facilities, where approximately 30% of their blood volume is extracted through a needle inserted into a joint in the carapace. The animal survives the procedure in most cases and is returned to the ocean. It is estimated that between 500,000 and 1 million horseshoe crabs are bled annually for pharmaceutical purposes. A synthetic alternative called RFC has been developed and validated by the scientific community, but its regulatory adoption advances slowly because natural LAL remains the established standard and the industry resists change with the argument of the familiarity of historical data. Limpet sea snails have teeth made of the strongest biological material on Earth, surpassing Kevlar. Most people who have ever walked along a rocky beach at low tide have encountered a limpet without knowing what it was. They are those flattened mollusks with conical, smooth shells that adhere to rocks with a force that seems disproportionate to the animal's size. Trying to pull a limpet off a rock with your hands is surprisingly difficult. The animal engages its foot musculature with a pressure per area that rivals many synthetic adhesives. But the most extraordinary mechanical feature of the limpet is not how it attaches to the rock. It is how it scrapes it. Limpets feed by scraping the biofilm of algae and cyanobacteria that grows on rocky surfaces. To do this, they use an organ called a radula, a ribbon-like structure similar to a tongue covered in rows of teeth. The radula scrapes back and forth over the rock in a rhythmic motion, removing organic material from the surface. In animals living in high-energy environments, such as surf zones where waves are strong and the substrate is granite or basalt, the abrasion is enormous. A tooth that could not withstand this continuous friction against rock would be worn down in hours. The solution that limpet evolution developed was to build teeth that are literally harder than the rock they scrape. In 2015, Professor Asa Barber from the University of Portsmouth published the results of tensile strength measurements performed on the teeth of the limpet species Patella vulgata in the journal Proceedings of the Royal Society using atomic force microscopy. The values found ranged between 3.0 and 6.5 gigapascals of tensile strength, with an average of 4.9 gigapascals. To put this number in context, spider silk, which until that study was considered the strongest biological material ever measured, reaches around 1.3 gigapascals. Kevlar, the synthetic material used in bulletproof vests, reaches approximately 3.6 gigapascals. High-performance carbon fibers are in the range of 4 to 7 gigapascals. Limpet teeth are at the top of this scale, matching or surpassing state-of-the-art engineering materials that took decades to develop. The material responsible for this strength is a mineral called goethite, an iron oxyhydroxide that forms in nanofilaments within the tooth structure. Each limpet tooth is a composite structure. High concentrations of oriented goethite filaments, occupying approximately 80% of the tooth's volume, are embedded in a protein matrix called chitin. Chitin is the structural polymer that also makes up the exoskeletons of insects and crustaceans and is relatively flexible on its own. Goethite is extremely hard and rigid. Together, in the specific proportion and orientation in which they exist in the limpet tooth, they create a composite whose mechanical properties surpass either of the two materials individually. Great white sharks can sense a drop of blood 5 kilometers away. The great white shark occupies a space in the collective imagination that blends fascination and terror almost perfectly. It is the ocean's supreme predator, the animal that inspires films that turned beaches into places to be avoided during the summer. The symbol of something that hunts not out of immediate hunger, but through a presence that seems intelligent and relentless. This reputation is rooted in real facts about its physiology, and no fact about its physiology is as frequently cited, and as frequently misunderstood, as its ability to detect blood in the water. The drop of blood at 5 kilometers is a myth. It is a powerful image, a hyperbole that has circulated in books, documentaries, and beach conversations for decades, but it does not hold up to careful examination. What is real, and what makes the great white shark so formidable as a hunter, is the existence of a specialized sensory system called the lateral line. a set of organs distributed along the animal's flank that detect vibrations and pressure differences in the water, and the ampullae of Lorenzini, pores sensitive to electric fields located on the snout and around the mouth. The ampullae of Lorenzini are particularly remarkable. They are cavities filled with collagen gel that connect directly to the nervous system and detect tiny electrical potentials generated by the movement of muscles and nerves in live prey. A wounded fish, a bleeding mammal, or any living creature emits a characteristic electric field that propagates through the water with surprising efficiency. The great white shark can detect voltage differences on the order of nanovolts per centimeter at distances of several meters. It is enough for the animal to locate prey, even if it is buried in the sand or hidden behind obstacles, guiding the final strike when vision and smell are no longer sufficient. The shark's sense of smell is what fuels the drop of blood myth. The great white shark has lateral nostrils, not frontal ones like ours, which function exclusively as olfactory organs and not for respiration. Water enters through the nostrils, passes over sensory plates rich in olfactory receptors, and exits. It is estimated that a great white shark can detect concentrations of amino acids and other chemical compounds associated with blood or damaged tissue in the range of 1 part per million. In concrete terms, this means a single milliliter of human blood diluted in an Olympic-sized swimming pool could be detected if the shark were directly in the water current carrying it. But dilution in an open ocean, with currents and turbulence dispersing the chemical plume, reduces the effective distance to hundreds of meters, not kilometers. What actually happens when a great white shark detects blood is a process of sensory triangulation. Smell detects the presence of chemical compounds down current. The lateral line detects vibrations and pressure changes. The ampullae of Lorenzini locate the source's electric field. Vision, sharp even in murky waters, confirms it at the end. It is a multimodal system that makes the shark efficient, not magical. And efficiency is what inspires fear. An animal that can find wounded prey at a distance sufficient to initiate a targeted search, and that can track it with surgical precision when nearby. Orcas are not whales. They are the largest members of the dolphin family. The common name orca or killer whale carries a weight that comes from the tradition of whaling. Whalers of the 19th and early 20th centuries observed orcas attacking larger whales, including gray whales with calves, and labeled the behavior as murder. The name stuck, and with it came the association of the orca with whales, a categorization that seems intuitive at first glance. It is large, lives in the ocean, eats meat, it must be a predatory whale. But taxonomy, which organizes life according to evolutionary relationships rather than superficial similarities, tells a different story. The orca is not a whale. It is a dolphin, the largest living dolphin. Dolphins and true whales belong to the superfamily Odontocidae, the toothed cetaceans, which split from the Mysticidae, baleen cetaceans like the blue whale and humpback whale, about 34 million years ago. Within the Odontocetes, orcas belong to the family Delphinidae, the same family as long-beaked dolphins, bottlenose dolphins, spotted dolphins, and coastal porpoises. It is the largest family of marine mammals with approximately 37 species, and the orca, with its 9 meters in length and up to 10 tons of weight in adult males, is the pinnacle of size within it. The confusion comes from the scale. Dolphins are medium-sized animals in the popular imagination. The bottlenose dolphin that interacts with swimmers on the coast of Brazil or Florida, the circus animal jumping through hoops. But the Delphinidae family includes a range of sizes from the 1.7-meter Maui dolphin to the orca, and anatomical and behavioral similarities confirm the family relationship. All Delphinidae species have conical teeth instead of the baleen plates of the Mysticetes. All use echolocation to hunt and navigate. All have complex social structures with distinct vocal dialects by population. All practice cultural behaviors transmitted between generations, from specific hunting techniques to playing with objects or bubbles. Orcas exemplify these characteristics on an enlarged scale. Their populations are genetically distinct to the point of being considered separate ecotypes. Pacific Northwest residents that feed exclusively on salmon, transients that hunt marine mammals in small, silent groups, offshores that live far from the coast and eat sharks, and Antarctic populations with unique dialects and hunting strategies for each clan. Each ecotype has its own vocal dialect, learned from parents and transmitted to offspring. so distinct that orcas from different groups seem not to recognize each other. It is cetacean culture in action. The orca's bite is a direct consequence of this dolphin identity. With 40 to 56 conical teeth up to 10 centimeters long, designed for grasping and tearing rather than crushing or filtering, the orca bites to kill and dismember. Unlike the true whale, which swallows prey whole or filters krill, the orca uses its teeth as tools of surgical precision. Observations have documented orcas removing the liver from broad-nosed seven-gill sharks, the tongues from gray whales, and the tongues and lips from humpback whales, with efficiency that suggests learning and practice. It is the bite of a dolphin that grew to the size of a small whale. Seahorses dance together every morning to reinforce their lifelong bond. The seahorse is one of the most immediately recognizable animals in the ocean. Its upright body, its head reminiscent of a miniature horse, and its prehensile tail that wraps around anchors or algae to stabilize itself against currents. But what makes the seahorse truly unique is not its shape. It is its reproduction. Seahorses are one of the few groups of animals in which the male carries the embryos until birth, in an abdominal marsupium that functions as an external uterine pouch. It is the male that gives birth, releasing live and fully formed offspring in swarms of up to 1,000 individuals per gestation. But this inversion of traditional reproductive roles is accompanied by another behavior that is equally extraordinary: lifelong monogamy, reinforced by a daily ritual of synchronized dancing. Male and female seahorses form stable pairs that last a lifetime. Once they unite, they stay together until death separates them, or until a partner disappears due to accident or illness. And every day, at dawn, they perform a ritual that lasts between 5 and 10 minutes and seems designed to reaffirm the bond that unites them. The pair swims in perfect synchrony, side by side, in undulating movements that make them rise and fall together in the water column. They spin around each other in tight spirals, synchronizing speed and direction with precision that suggests constant communication. The female transfers the eggs to the male's marsupium through an ovipositor tube, and the male fertilizes them at the moment of transfer. Then the ritual ends, and the pair separates to forage individually during the day. What makes this ritual particularly fascinating is that it is not just a prelude to copulation. It is performed every day, regardless of the stage of the reproductive cycle. Researchers who marked pairs of seahorses in Australian reefs and observed their behavior over months discovered that the rituals occurred religiously at dawn, with duration and complexity that did not vary significantly between fertile and infertile days. When a partner was experimentally removed from the environment and then returned, the pair performed the ritual with increased intensity, as if re-establishing the interrupted bond. When a new individual was introduced, the rejection behavior was immediate and decisive. This monogamy is not just behavioral. There is genetic evidence that seahorses avoid multiple reproductive partners within a season. DNA analyses of wild populations show that most offspring from a male have the same mother, and vice versa. It is a reproductive strategy that seems counterproductive at first glance. In an environment with high egg and offspring mortality, diversifying partners would increase the chances of genetic success. But seahorses seem to have evolved to prioritize the quality of parental care over the quantity of partners. The male, carrying the embryos in his marsupium, protects them, oxygenates them, nourishes them with glandular secretions, and releases them only when they are ready for independent life. A single, reliable partner maximizes the success of this process. The snapping shrimp creates a heat bubble that reaches the temperature of the sun for a microsecond to stun prey. The snapping shrimp, also known as the pistol shrimp or Alphiidae, is a crustacean that lives in coral reefs around the tropical world, with a body a few centimeters long and a specialized claw that is approximately half the size of its body. This claw does not bite, it snaps. And what happens when it snaps is one of the most violent mechanical events in nature on a small scale. A physical process so extreme that it involves cavitation, supersonic shock, plasma, and temperatures that exceed the surface of the sun for fractions of a second. The mechanism begins when the shrimp closes its specialized claw with enough speed to generate an acceleration of 30 meters per second squared. The claw does not make direct physical contact with the prey. Instead, the movement creates a water current that separates from the surface of the claw, forming a low-pressure cavity, a microscopic vacuum bubble. This bubble collapses almost immediately, in less than a millisecond, when the pressure of the surrounding water compresses it back. The collapse is so fast and violent that it generates a supersonic shockwave, audible as a loud snap, that can be heard meters away, and is the origin of the animal's common name. Researchers from the University of Twente in the Netherlands and the National University of Singapore used high-speed photography and spectral analysis to measure what happens inside this cavitation bubble. They discovered that the collapse compresses the gas and vapor inside the bubble to such an extent that the local temperature reaches approximately 4,700 Kelvin, or about 4,400 degrees Celsius, for a microsecond. For reference, the surface of the Sun has a temperature of 5,500 degrees Celsius. The Sun's core is 15 million degrees. But inside this bubble, just a few millimeters in diameter, for a fraction of time shorter than any human blink, conditions approach stellar hell. The heat ionizes the gases inside the bubble, creating a plasma that emits bright white light, detectable as a flash in ultra-fast photography. When the plasma cools and the bubble collapses completely, the resulting shockwave reaches pressures of up to 80 kilopascals, sufficient to stun or kill small prey such as other crustaceans, worms, and even small fish. The shrimp uses this snap not only for hunting but also for communication and territorial defense, with patterns of frequency and duration that vary between individuals and populations. The phenomenon is called pistol shrimp sonoluminescence, and it is one of the few known examples in nature of plasma generation by purely biological mechanical means. The shrimp's claw is a weapon that combines mechanics, hydrodynamics, and thermodynamics on a microscopic scale, producing an event that, in any other context, would require particle accelerators or controlled explosives to be recreated in a laboratory. There are glass sponges that build skeletons of pure silica, resembling crystal gardens. When one says reef, the image that immediately comes to mind is coral, the colorful calcareous structure of tropical reefs, inhabited by fish and crustaceans, exhaustively photographed, a symbol of marine biodiversity and ecological fragility. But there are other types of reefs in the ocean, built by other builders with other materials at other depths, and which have a physical beauty so different that the appropriate metaphor is not the tropical garden but the crystal garden. Glass sponges belong to the class Hexactinellida, a group of sponges that use silica dissolved in seawater to build their skeletons instead of limestone or organic proteins. Silica is the same compound that forms quartz, rock crystal, and common glass. And glass sponges work with it at the nanoscale, producing structures called spicules, small fragments of biogenic silica in shapes of 6 points, rods, stars, and hooks that weld to one another in a complex three-dimensional architecture. The result is a skeleton that, when the living tissue is removed, looks literally made of glass. Approximately 80% of a glass sponge's body is skeleton. Living tissue exists as a thin layer over this mineral structure, a film of life over an architecture of silicon. When the sponge dies, the skeleton remains. And when new sponges grow on the skeletons of the old ones, accumulating generation upon generation over millennia, the result is a silica reef, a biogenic building that can be dozens of meters high and kilometers long, built entirely of biological glass. Glass sponge reefs were considered extinct by scientists until their live rediscovery in 1987 off the coast of British Columbia, Canada. Before that, they were known only from fossils from the Jurassic period, more than 150 million years old, and the widespread assumption was that the reef-building species had disappeared along with the mass extinctions at the end of the Mesozoic. When submersibles identified living structures off the Pacific Northwest coast at depths between 90 and 250 meters, it was one of the most notable marine biology rediscoveries of the 20th century. A type of ecosystem thought extinct for millions of years was right there, growing slowly in cold, silica-rich waters. The interior of a glass sponge reef is an extraordinarily complex microhabitat environment. The interlocking structures of the spicules create spaces and channels at multiple scales, from millimeters to meters, where shrimp, worms, copepods, and small fish find refuge, food, and surfaces for attachment. The sponge itself continuously pumps water through its channel system, filtering bacteria and organic particles with an efficiency that researchers have compared to high-precision industrial filters. And in doing so, the sponge processes volumes of water that have a measurable impact on the local chemistry of the water column around the reef. The optical structure of the silica skeleton has a property that fiber optic engineers have studied with interest. The silica filaments produced by glass sponges guide light in a way analogous to manufactured fiber optics, but with superior mechanical flexibility that synthetic glass fibers do not achieve because they were produced at high temperature, a process that introduces crystalline brittleness. The biogenic silica of sponges forms at the ambient temperature of the ocean floor, and the resulting molecular organization has distinct mechanical properties. It is another instance where biology, having had hundreds of millions of years to experiment, arrived at a solution that human engineering is still trying to match. Albatrosses have special glands above their eyes to filter salt from seawater and drink it. The albatross spends most of its life in the air over the open ocean. It can fly for years without touching land, using air currents above the waves to glide with an absolute minimum of muscular effort, sleeping in flight, and feeding by briefly landing on the surface to capture fish and squid. It rarely comes to shore. It rarely drinks fresh water. And the ocean it flies over offers an abundance of water with a salinity that would make a human who drank it increasingly dehydrated, as human kidneys cannot process salt in concentrations above 2% without consuming more water in the process of excretion than was ingested. The albatross has a solution that human naval biology took centuries to understand and that engineering has not yet replicated with the same efficiency and lightness. Desalination nasal glands. Located at the top of the skull, above the eyes, in cavities that run along the base of the bill, these glands are active excretion organs that work continuously when the animal is at sea. They receive blood from the systemic circulation, extract sodium and chloride ions with an efficiency that surpasses the kidney's concentration capacity, and secrete a highly concentrated saline solution that runs through the nasal ducts to the outside of the bill, where it forms droplets that drip or are actively expelled through the tubular nostril that gives the albatross that characteristic bill profile with cylinders above the nostrils. The cellular mechanism of this extraction is an active transport process. Specialized carrier proteins in the gland cells use metabolic energy to move sodium and chloride ions from the interior of the cells to the lumen of the ducts, against the concentration gradient work that requires ATP expenditure but frees the blood of salt with an efficiency that avian kidneys could not achieve alone. The nasal gland produces a saline solution that can have a salinity 3 times higher than the animal's blood, which means the amount of water needed to excrete each gram of salt is much lower than it would be if the kidneys did the work. The albatross drinks seawater and comes out of the process hydrated because the gland can concentrate the salt enough for the net balance to be positive. Other marine animals have versions of this gland. Sea turtles have modified tear glands that excrete salt as a thick liquid that runs from the eyes, giving turtles that nest on the beach the appearance of crying. Marine iguanas from the Galapagos have nasal glands that function similarly to the albatrosses and periodically sneeze the excess salt in jets that form white deposits on their heads and snouts. Sea snakes, sharks, and several species of seabirds have variations of the same system. It is a solution that evolution found independently in different lineages every time a warm-blooded terrestrial animal wanted to colonize the ocean without changing its internal fluid. The characteristic smell of the sea comes from a gas called DMS, produced by bacteria that digest plankton. There is a familiar moment for anyone who has traveled to the coast by car or train. That instant, even before seeing the water, when the smell arrives. It is an immediately recognizable scent, difficult to describe with precision but impossible to confuse with any other. It has a slightly pungent, almost mineral component, which mixes with salt and the breeze, triggering in many people a sense of anticipation, of arrival, of something the body recognizes as familiar even if the mind doesn't know exactly why. This smell has a chemical name, a production mechanism, and a story that connects microscopic bacteria to the planet's climate. The substance responsible for the characteristic aroma of the ocean is called dimethyl sulfide, or DMS. It is an organic sulfur-containing gas that forms in the ocean and evaporates into the atmosphere, where it is carried by the wind and reaches the nostrils of anyone near the sea. The ocean releases tens of millions of tons of DMS per year, making it one of the most voluminous gaseous fluxes of any non-inorganic chemical substance that the ocean emits into the atmosphere. The production chain begins with phytoplankton, microscopic photosynthetic organisms that inhabit the upper illuminated layers of the ocean produce, as part of their internal metabolic processes, a compound called DMSP, dimethylsulfoniopropanate. DMSP has various functions within phytoplankton cells. It acts as an osmolyte, helping cells regulate their internal water balance relative to the salinity of the surrounding water. It works as an antioxidant, and it possibly acts as a chemical defense substance against grazers. While the phytoplankton is alive and intact, DMSP remains inside the cells. When the phytoplankton dies, when cells are damaged, or when zooplankton grazes and grinds the phytoplankton into fragments, DMSP is released into the water. And that is where the bacteria come in. Marine bacteria that inhabit the surface layers of the ocean consume DMSP as a source of carbon and sulfur, and in approximately 10% of these consumption reactions, the final product is DMS. The other, more common metabolic route processes DMSP into compounds that remain in the aquatic environment and re-enter the microbial food web. But when the route that produces DMS is followed, the gas forms, is poorly soluble in water, and rises into the atmosphere with relative ease. The smell that reaches a beach is this gas, produced by a process involving phytoplankton generating a compound for its own metabolic reasons, zooplankton grazing and releasing that compound, and bacteria transforming it into a gaseous molecule that evolution never designed to make smells, but which the olfactory receptors of marine mammals, and eventually humans, learn to associate with the ocean. The sea smell that evokes childhood memories, that makes the heart race slightly before seeing the waves, is a bacterial byproduct of a carbon and sulfur cycle that exists completely independent of any olfactory function. But DMS has a dimension that goes far beyond smells. In the atmosphere, it is oxidized into sulfur dioxide and then into sulfuric acid, which forms microscopic particles that serve as nuclei for water vapor condensation. In other words, the DMS produced by the ocean stimulates the formation of clouds over the open ocean, and these clouds reflect solar radiation back into space, influencing the Earth's energy balance. The ocean literally perfumes the air with a substance that helps regulate the climate. Every time someone smells that characteristic scent upon reaching the coast, they are smelling a gas that connects the metabolism of microscopic phytoplankton to the formation of oceanic clouds. The smell of the sea is, among other things, the smell of the climate happening. Fish cough to clear their gills of sediment and particles. Coughing is a reflex. In mammals, it is triggered by receptors in the larynx and bronchi that detect irritants, particles, excessive mucus, or anything obstructing the airways. The result is a sudden contraction of the diaphragm and expiratory muscles that generates a high-speed airflow capable of expelling the irritant. It is a protection mechanism for the respiratory tract, and it is so fundamentally linked to air breathing that it seems difficult to imagine an aquatic equivalent. But fish have gills, and gills can accumulate sediment and particles. And when they do, fish perform something that researchers call, without embarrassment, a cough. The mechanism is technically called branchial cleaning or a gill purge. It is an interruption in the fish's normal ventilatory cycle, which generally consists of rhythmically opening the mouth to admit water and the coordinated closing of the opercula, the flaps that cover the gill chambers on both sides of the head, to force water to pass through the gill filaments where gas exchange occurs. In a cough, this pattern is suddenly reversed. The opercula close abruptly and open in a sequence that generates water flow in the opposite direction to normal, sweeping the surface of the gills from the inside out and expelling accumulated particles. In clear water conditions, fish cough periodically as maintenance behavior, even without noticeable accumulation. In murky water or water rich in suspended sediment, the frequency of coughing increases proportionally to the concentration of particles. Researchers from the U.S. Environmental Protection Agency and various universities have used fish cough frequency as a bioindicator of water quality. When fish exposed to a certain water sample increase their branchial cleaning rate above the normal baseline, it indicates the presence of chemical or particulate irritants above tolerable limits. The sensitivity of the reflex is remarkable. Studies with bluegill sunfish and other laboratory species showed that the cough rate increases when fish are exposed to treated industrial and municipal effluents, even when these effluents do not contain visible particles, suggesting that dissolved chemical compounds also trigger the reflex through chemical receptors in the gill tissues. In fish that normally inhabit clear waters, such as clownfish from tropical reefs, even relatively low concentrations of suspended sediment cause structural damage to the gills and increase the branchial cleaning rate defensively. Shark skin is covered by denticles that act like tiny teeth, reducing drag and preventing the growth of fouling organisms. The skin of a shark, touched the wrong way, is immediately identifiable as different from everything intuition expects. Touched from tail to head, or laterally, it feels as rough as medium grit sandpaper. Touched from head to tail in the direction of water flow as the animal swims, it is surprisingly smooth. This directional texture asymmetry is the most immediate clue to what exists on the surface. Not scales in the conventional sense of the term, but denticles, individual structures composed of dentin and enamel, anchored in the dermis and projecting outward like tiny teeth. Denticles, also called placoid scales, are evolutionarily the same structures as teeth. This is not a metaphor. Sharks are chondrichthyans, cartilaginous fish, and in their group, teeth and skin structures share the same embryological origin, the same materials, and the same developmental processes. A shark's teeth are, in an evolutionary sense, specialized denticles that migrated to the mouth and increased in size. And skin denticles are, in a sense, teeth distributed throughout the body. A shark's skin is covered in teeth. The shape of each denticle is not uniform. It varies between species and between body regions within the same species, with geometries that were shaped by evolution for specific functions. In general, denticles are keel-shaped, with one or more longitudinal ridges running in the direction of the water flow and edges that taper toward the back. When water flows over this texture during swimming, the denticles modulate the turbulent boundary layer, the region of water immediately adjacent to the shark's surface where friction is highest. The ridges of the denticles organize microscale vortices that reduce friction drag, especially at moderate swimming speeds, allowing the shark to move with less energy expenditure than it would if its surface were smooth. The anti-fouling function, resistance to the growth of organisms like algae, barnacles, and bryozoans on the surface, is equally important. Any vessel or submerged structure without specific protection quickly accumulates a community of fouling organisms that increases drag and requires constant maintenance. Shark skin, with its microscopic denticles of hard enamel and non-porous surface, offers a topography that fouling organisms have difficulty colonizing. Barnacle larvae and algae spores prefer smooth surfaces or specific textures that facilitate permanent adhesion. The texture of the denticles, with their ridges and valleys on a micron scale, disrupts the colonization process effectively enough that healthy sharks rarely exhibit fouling growth on their skin. Engineering has copied this principle. Hull paints for ships and aircraft turbines were developed with inspiration from the texture of shark denticles, seeking to reduce drag by manipulating the boundary layer without adding mass or active components. Competition swimsuits developed for the 2008 Beijing Olympics incorporated a surface with an artificial denticle pattern, which provoked enough controversy for FINA, the International Swimming Federation, to subsequently ban high-tech fabrics that conferred verifiable aerodynamic and hydrodynamic advantages. The ban was itself a recognition of effectiveness. Shark skin works well enough to change results in elite competitions. More sunlight is absorbed in the first 10 meters of the ocean than in the entire Earth's atmosphere. The Earth's atmosphere is dense with gases, aerosols, dust particles, and water vapor, and anyone who has seen a sunset knows it has visible effects on the light passing through it. The red and orange of twilight are a consequence of the preferential scattering of shorter wavelengths by the air, which makes direct light appear redder when it travels a longer path through the atmosphere. Clouds block and scatter. Ozone molecules absorb ultraviolet. The atmosphere is, in many ways, an active filter of solar radiation. And yet, when sunlight hits the ocean surface without the interference of clouds, only 2% of it is reflected back. The other 98% enters the water. And in the first few meters of the oceanic column, this energy is absorbed with an efficiency that the atmosphere, with all its density and chemical complexity, cannot match in equivalent distance. The first 10 meters of the ocean absorb more solar energy than the entire atmospheric column of hundreds of kilometers that the light traveled to get there. The physical reason lies in density and composition. Water is 800 times denser than air. Each meter of water is equivalent, in terms of the mass of material light passes through, to 800 meters of air. But beyond density, water absorbs specific wavelengths of the solar spectrum with an efficiency that goes far beyond what any common atmospheric gas can do in a comparable distance. Near and mid-infrared, which represent a substantial fraction of total solar energy, are absorbed almost completely within the first few centimeters to a few meters of depth. Red disappears in the first few meters. Orange and yellow in the following tens of meters. These wavelengths of high thermal energy do not reach deep. The practical consequence is that the surface layer of the ocean works as an extraordinarily efficient solar collector. All the thermal energy the ocean absorbs from solar radiation enters through this thin surface window. It is this energy that heats the surface mixed layer, fuels the evaporation that generates precipitation on land, and which, as we have already seen, represents the heat the ocean has accumulated over the recent decades of climate change. The ocean absorbs solar energy not through its depth, but through its surface, and the upper 10 meters are where most of this transaction happens. There is also a geographic asymmetry that amplifies this fact. Tropical oceans, where sunlight hits the surface more perpendicularly, absorb solar energy with maximum efficiency. The atmosphere that this light passes through before hitting the surface in the tropics is thinner than at the poles, where the tilt makes the light travel a longer path through the air before reaching the ocean. This means the oceanic tropics receive most of the planet's solar energy and absorb it mainly in the first few meters of water, creating the highest surface temperatures and fueling the convection currents that redistribute this heat to higher latitudes. In Mexico, there are rivers of sand that fall into underwater abysses like terrestrial waterfalls. Jacques Cousteau called the waters around Cabo San Lucas, at the southern tip of the Baja California Peninsula, the aquarium of the world. This reputation comes from an extraordinary biology. The confluence of cold Pacific currents and the warmer waters of the Gulf of California creates a diversity of habitats in a single place that gathers species that normally live at very different latitudes. But the feature that made Cousteau personally dive there and later film what he found was not a fish or a reef. It was a waterfall at the bottom of the sea. Inside Cabo San Lucas Bay, at a depth of 30 meters, there is a rift in the ocean floor that marks the edge of the San Lucas Canyon, an underwater ravine that drops abruptly for more than 300 meters before continuing to greater depths. And over this edge, continuously and visibly, flow rivers of fine sand that arrive from the beach and the shallow bottom carried by currents, accumulate at the canyon's edge, and plunge down the precipice just as a terrestrial waterfall would plunge over a cliff, with the difference being that the medium in which all this happens is water, and the substance falling instead of water is sand. The mechanism begins at the beach. Waves arriving at Cabo San Lucas carry fine sand sediment that resuspends and transports along the shallow bottom into the bay. Bottom currents and the progressive slope of the seabed lead this sediment toward the canyon. When the sand accumulates at the edge of the underwater cliff, gravity does the rest. The density of the sand is much greater than that of the surrounding water, and it slides down the precipice in a coherent flow, a river of solid particles descending a vertical rock wall underwater, with the unmistakable visual appearance of a waterfall in slightly slow motion. The phenomenon was discovered in 1959 by Francis Shepard, a researcher from the Scripps Institution of Oceanography, during an expedition studying bottom currents and underwater sediment transport. Shepard was impressed enough to document the sandfalls in a scientific publication, and it was Cousteau who later filmed the site and popularized it for audiences beyond oceanography. Today, the Sandfalls dive site in Cabo San Lucas is one of the most visited in Mexico, with divers descending to 30 meters to watch the flow of sand sliding down the cliff, sometimes in continuous currents, other times in rhythmic pulses that respond to the movement of the waves on the surface above. The San Lucas Canyon works as a sedimentary transport duct connecting the beach to the abyssal floor. Sand that was on a beach can, in a matter of hours or days, be transported to depths of hundreds of meters, deposited on the canyon floor, and incorporated into deep sediments where it will remain for millennia. This process is called a turbidity current when it occurs on a larger scale and is responsible for much of the sedimentary deposits that accumulate at the foot of continental shelves around the world. Cabo San Lucas offers an accessible and visible version of a process that is normally invisible because it occurs at intangible depths. The Milky Seas phenomenon creates a milky glow so vast that it is visible to astronauts in space. There is a form of bioluminescence that sailors described for centuries using the language of the supernatural. Not the flash that occurs when a wave breaks at night and disturbed plankton emit blue light for fractions of a second. Not the glow of a pulsing jellyfish. Something completely different in scale and quality. A white, uniform, stable luminescence that covers the ocean surface in all directions to the horizon, persisting for hours and days, making the ocean look full of spilled milk or lit from below by a white-green neon light, transforming nighttime navigation into an experience that sailors across multiple centuries and cultures described as the most awe-inspiring they had ever experienced at sea. This phenomenon has a scientific name, Milky Seas, and it has a cause that took a long time to identify with any certainty, because the events are rare, unpredictable, and occur mainly in the Indian Ocean and the Western Pacific, far from the research centers that would have the resources to study them systematically. The hypothesis most supported by evidence is that Milky Seas are caused by population explosions of bioluminescent bacteria, mainly Vibrio harveyi, which establish high-density colonies associated with specific microalgae blooms on the oceanic surface. The difference between this type of bioluminescence and that of plankton that flashes with mechanical disturbance is fundamental. These bacteria emit light continuously and autonomously, without needing a stimulus. When their density hits certain thresholds, a quorum-sensing phenomenon, the perception of population density through chemical signals, causes the entire colony to light up simultaneously. Each individual bacterium emits a tiny amount of light, but when trillions of them are on the ocean surface, the integrated effect is a diffuse luminescence covering areas of tens of thousands of square kilometers. In 2005, researchers published in the journal PNAS the first satellite detection of a Milky Seas event. Using nighttime images from the low-light imaging sensor of a U.S. meteorological satellite, they identified an event in the northwestern Indian Ocean that persisted for 3 consecutive nights and covered an area of approximately 15,400 square kilometers, slightly larger than the state of Connecticut. The detection was confirmed by the crew of a ship sailing through the region on the first night, who reported the phenomenon consistently with the satellite images. It was established that the glow was real, stable, and intense enough to be detected by orbital sensors hundreds of kilometers high. A systematic review of satellite data from the VIRES sensor between 2012 and 2021 identified 12 Milky Seas events, all in the Indian Ocean and Western Pacific. This is a frequency of approximately 1 event per year in the area covered by this data, suggesting that the phenomenon is more common than historical sailors' accounts indicated, but still rare and geographically concentrated enough to escape the knowledge of most people. The conditions necessary for its formation are still not fully characterized. Specific ocean surface temperature, nutrient concentrations, the presence of the right host microalgae, and some population trigger for massive bacterial growth all seem necessary, but no current model can predict where and when the next event will occur. The 1883 eruption traveled across the ocean and was heard 5,000 kilometers away, being the loudest sound ever recorded. On the morning of August 27, 1883, on a volcanic island in the Sunda Strait between Java and Sumatra, in what was then called the Dutch East Indies, a series of eruptions culminated at 10:02 a.m. in an explosion of a magnitude that has no documented precedent in human history in terms of sound volume. Krakatoa, a volcano that had been in moderate activity for months, went into catastrophic collapse when the sea penetrated the overheated magma chamber system, generating a reaction that turned a mountain into dust distributed through the stratosphere and sent an acoustic pressure wave traveling through the planet's atmosphere. The shock wave generated by the main explosion propagated through the air at the speed of sound, approximately 340 meters per second, in all directions from the point of origin. Barometers around the world recorded the passing of this pressure wave. And not once. The wave circled the globe completely and was recorded arriving from opposite directions to the starting point, then circling again and again. Barometric records show the wave's signature passing through weather stations worldwide at least 7 times over the following days. The distance at which the sound was heard directly as audible sounds by human ears was approximately 5,000 kilometers. To give a geographic reference, this corresponds to the distance between the Sunda Strait and the city of Yangon, Burma, or the equivalent of hearing an explosion in New York clearly from Los Angeles plus half the way back. Listening stations on Rodriguez Island, a small British territory in the Indian Ocean 4,800 kilometers from Krakatoa, recorded the sound as a series of artillery flashes to the north, which local administrators reported to British authorities as possibly an unexplained naval disturbance. The sound intensity at 160 kilometers away was estimated at 180 decibels. For a scale reference, the pain threshold for human ears is 120 decibels. A jet engine at 30 meters produces approximately 140 decibels. A nearby lightning strike produces between 120 and 130 decibels. The decibel scale is logarithmic, meaning each 10 decibel increase corresponds to 10 times more acoustic intensity. 180 decibels represents an intensity 1 million times greater than the human pain threshold. To anyone within 16 kilometers of the explosion point, the sound would cause immediate permanent hearing loss. The ocean played a crucial role in the propagation. The pressure wave generated by the explosion coupled with the ocean surface, exciting a tsunami wave that propagated outward from Krakatoa in growing circles. The tsunami, with heights reaching 30 meters as it hit the coasts of Java and Sumatra, killed more than 36,000 people, the vast majority of the approximately 40,000 total victims of the event. The sound traveled through the air, the destruction traveled through the ocean, and the volcanic ash particles that Krakatoa launched 80 kilometers high remained suspended in the stratosphere for years, causing red and orange sunsets worldwide for the following 18 months and reducing the average global temperature by 1.2 degrees Celsius for more than a year. The underwater volcano Loihi is growing in Hawaii and will become a new island in tens of thousands of years. Hawaii exists because there is a hotspot in the Earth's mantle, a plume of superheated rock that pierces the oceanic crust and feeds surface volcanoes. What makes this hotspot unusual is not its existence. Hotspots exist in various places on the planet, but the fact that the Pacific oceanic plate moves slowly over it, at a pace of approximately 7 to 10 centimeters per year, creating a series of volcanoes that are abandoned by the hotspot as the plate carries them away. The result is a chain of islands and seamounts stretching more than 6,000 kilometers toward the northwest, with the older islands already eroded below the sea surface and transformed into atolls and seamounts, and active volcanism concentrated in the newer islands closer to the hotspot. The newest link in this chain is not above sea level. Yet, Loihi is an active seamount located approximately 30 kilometers southeast of the coast of the Big Island of Hawaii, with its peak submerged about 975 meters below the surface. It began forming about 400,000 years ago when the ocean floor in this region began passing over the Hawaiian hotspot, and since then it has grown through successive eruptions that accumulate basalt layer by layer. Today, it is already taller than Mount St. Helens in the United States when counted from its base on the ocean floor. Loihi is volcanologically active. In 1996, a sequence of more than 4,000 earthquakes in a week preceded a series of eruptions that created new lava flows at the top of the mount and collapsed part of the summit crater, forming a new pit called Pele's Pit, named after the Hawaiian goddess of volcanoes. This event was enough for the USGS to establish continuous seismic monitoring, and since then, submersible instruments have monitored both seismic activity and hydrothermal emissions at the mount summit. The estimate of when Loihi will emerge above sea level is uncertain. Using the average growth rate observed in other volcanoes of the Hawaiian chain, geologists estimate between 10,000 and 100,000 years. This tenfold range of uncertainty reflects the nature of the problem. Volcanic growth is not linear. Intense eruption periods can build meters of height in weeks. Long dormancy periods might contribute nothing. Wave erosion and gradual subsidence of the plate under the mount's own weight partially offset the growth. The calculation is one of geological probability, not precision engineering. When Loihi finally emerges, it will not happen quietly. The way oceanic volcanic islands arise above the sea is explosive in the most literal sense. When erupting lava encounters reduced pressure near the surface and then contact with seawater, steam expansions and reactions between magma and water generate phreatomagmatic eruptions of considerable violence. The first islands of Hawaii were like this. Not mountains that emerge gently, but explosions that build shallow platforms which progressively consolidate and stand above the waves. The entire Hawaiian chain is a visible geological timeline. Kauai, the oldest island, is 5.1 million years old, and its original peaks have been eroded to less than half their original height. The Big Island, the newest of the inhabited islands, is between 0.4 and 0.7 million years old and still has active volcanoes adding new land. And Loihi, under 975 meters of ocean, is still in the underwater phase that all other islands in the chain have already completed. In 10,000 years, or perhaps in 100,000, some being inhabiting the Earth at that time will watch a new island appear on the horizon southeast of Hawaii. The ocean will swallow the lava. The steam will rise, and the hotspot will have made one more island. In the middle of the ocean, a tsunami can be just 30 centimeters high and pass completely unnoticed by ships. The word tsunami evokes images of walls of water several meters high rushing over coastal cities, sweeping away buildings and carrying off vehicles. And these images are real and documented. But this destruction is a coastal phenomenon, the final chapter of a story that begins in a completely opposite way, with something so small and so gentle that a ship can pass directly over it without any crew member noticing anything out of the ordinary. The secret lies in the wavelength. A common wind wave in the open ocean has a wavelength, the distance between one crest and the next, of a few meters to a few tens of meters. A tsunami has a wavelength of 100 to 800 kilometers. This difference in scale changes everything. A wind wave passes under a ship in fractions of a second and makes it rise and fall visibly. A tsunami passes under the same ship in 10 to 45 minutes, raising and lowering the hull on an incline so gradual and so slow that it is indistinguishable from the normal state of the sea. The ship rises a palm's width. Then it goes down. In 40 minutes, no one notices. In the open sea, a tsunami generated by a magnitude 9 earthquake might have only 30 to 60 centimeters of vertical amplitude while crossing the deep ocean. Part of the explanation lies in the physics of wave propagation in deep water. Wave speed is proportional to the square root of the depth. In an ocean 4,000 meters deep, a tsunami travels at approximately 700 kilometers per hour, the speed of a commercial jet. This incredibly high speed keeps the wave stretched horizontally, distributing its energy over enormous lengths with correspondingly small amplitude. What transforms this gentle wave into a wall of destruction is the coast. As the tsunami approaches shallow waters, the propagation speed decreases because the depth decreases. However, the total energy of the wave does not decrease. It is simply compressed into a smaller volume of water. The wavelength reduces from hundreds of kilometers to a few kilometers. The amplitude, to conserve the same energy in less space, grows in inverse proportion. A 30-centimeter wave in the open ocean can transform into 10, 20, or 30 meters upon reaching the coast, depending on the seafloor geometry and the shape of the bay. This process is called shoaling, and it is the same process that turns wind waves into surf on beaches, only on an incomparably larger energy scale. The 2004 Indian Ocean tsunami was recorded by seismic and tide monitoring stations worldwide during the hours it crossed the ocean before reaching the coasts. The data shows its amplitude in the open sea remained consistently small until the final tens of kilometers of approach. Surveillance camera videos on ships in the Strait of Malacca on December 26, 2004, show exactly what physics predicts. The sea goes from calm to slightly disturbed with a series of low and long swells, and then, minutes later, the coast a few kilometers away displays the catastrophe that the same waves produced upon encountering land. There are kilometer-long salt domes under the Gulf of Mexico that alter the chemistry of the surrounding water. 170 million years ago, during the Jurassic period, the Gulf of Mexico was a young and nearly closed sedimentary basin, much smaller than today, with restricted circulation and evaporation rates much higher than the influx of new water. Conditions were ideal for the massive-scale deposit of salt. As water evaporated faster than it entered, dissolved salts precipitated and accumulated at the bottom of the basin. Over millions of years, this process deposited a layer of salt that may have reached several kilometers in thickness in parts of the basin. Over time, other marine sediments were deposited over the salt, burying it under tons of material. But salt has a mechanical property that distinguishes it from most rocks. It is plastic under pressure. Instead of fracturing when compressed by the sediments deposited over it, the salt flows like an extremely viscous fluid along paths of least resistance. When the thickness of overlying sediments creates asymmetric pressure, the salt underneath begins to migrate laterally and upward through fissures and planes of weakness, forming structures called salt diapirs or salt domes that can rise several kilometers through the sedimentary column and reach near or even the surface of the ocean floor. The Gulf of Mexico has hundreds of these structures, some with kilometers in diameter and projecting 10 or more kilometers above the original layer. Where salt domes come near the ocean floor or crop out on it, they create brine seeps, fluids extremely concentrated in salt that leak from the formations and accumulate on the ocean floor. This brine is so dense, with salinity that can be 5 to 6 times higher than that of seawater, that it does not mix easily and forms underwater lakes and rivers on the seabed, bodies of water with a defined surface within the ocean. Algae and plankton do not survive in this hypersaline brine. However, highly specialized chemosynthetic communities colonize the edges of these brine pools, with mussels, polychaetes, and bacteria that derive energy not from photosynthesis but from the oxidation of methane and sulfur released along with the seeps. The altered chemistry around salt domes goes beyond the brine. The process of fluid expulsion by the domes also releases methane, hydrogen sulfide, and heavier hydrocarbons from the reserves trapped in adjacent sediments. These substances dissolve in the bottom waters and create chemical gradients that extend hundreds of meters above and around the seepage sites. Bacteria that oxidize methane and sulfate form visible microbial mats on the bottom, sometimes white, sometimes orange, covering square meters of substrate. Tube worms over a meter long grow in densities that look like miniaturized forests of rigid white tubes. The consequences for the oil industry are equally significant. Salt domes are geological structures under which hydrocarbons frequently accumulate because salt is impermeable and creates traps where oil and gas concentrate instead of migrating upward and dissipating. A large part of the oil reserves in the Gulf of Mexico is associated with these structures. The same salt that created unique chemosynthetic ecosystems at the bottom of the ocean is what made the Gulf of Mexico the most productive offshore extraction region in the United States for decades. The English Channel was a dry valley that connected the United Kingdom to France until a catastrophic flood 8,000 years ago. 12,000 years ago, England was not an island. It was a peninsula. The last ice age had removed so much ice from circulation that the average sea level was 120 meters below its current level, and what is today the North Sea and the English Channel was dry land. A region called Doggerland covered what is now the floor of the North Sea, extending continuously from the British coast to the European continent. It was a diverse landscape of rolling hills, marshes, forests, rivers, and coastal plains, inhabited by Mesolithic populations of hunter-gatherers who lived between coastal marine life and large inland mammals. Mammoths, giant horned elk, wild horses. Doggerland was rich in fauna and human populations who never needed a boat to walk from England to what is now Denmark. The end was gradual and then catastrophic. With the progressive melting of the ice caps of the late Pleistocene and early Holocene, the sea level rose persistently for millennia. The coasts of Doggerland slowly receded. What were once open plains became marshes. What were marshes became lagoons. What were lagoons became bays. And Mesolithic populations retreated to higher lands, likely without consciously recording that they were witnessing the shrinking of a world. But around 8,150 years ago, the gradual flooding was interrupted and then amplified by a catastrophic event. The Storegga Slide, an underwater landslide off the coast of Norway that was the largest landslide of the Holocene period. A mass of sediment and rock of 3,200 cubic kilometers broke away from the Norwegian continental margin and slid into the depths of the North Atlantic, displacing a volume of water sufficient to generate a tsunami of extraordinary proportions. The resulting wave swept across the British coast and what remained of Doggerland with enough force to penetrate 40 kilometers inland in some regions. Researchers from the University of Warwick and other British institutions who analyzed ancient DNA from North Sea floor sediments have reconstructed the ecology of Doggerland with surprising precision. Dense oak and hazel forests dominated the inland landscape, rivers with salmon ran to the sea, and evidence of human presence persists in the flint tools that trawlers occasionally bring to the surface. The British Museum has a collection of Mesolithic tools and animal bones dredged from the bottom of the North Sea. It is literal archaeology from the bottom of the sea. The southern part of what is now the English Channel followed a slightly different history. Geological studies of the channel floor have identified evidence of a separate flooding event prior to Storegga, which may have occurred around 450,000 years ago, when the ice or rock barrier separating the North Sea from a large southern lake basin would have catastrophically ruptured, creating the channel in a single large-scale flood. If this hypothesis is correct, the English Channel was not formed solely by the gradual rise in sea level, but by a combination of progressive erosion and abrupt rupture, and the Strait of Dover that today separates Dover from Calais by 34 kilometers was created by a flood that took days, not millennia. There are flows of hot water that rise from the ocean floor like invisible columns, the so-called hydrothermal plumes. Most rivers have two obvious attributes: horizontal direction and a visible surface. They rise from springs or come from mountains, run through valleys, accumulate in lakes, or flow into the sea. And throughout this journey, they are visible, palpable, and crossable by bridges. The rivers of the ocean floor that occupy us here have none of these attributes in a simple way. They flow vertically upward, they have no surface because they are inside another fluid, and most of them are invisible to the naked eye. What makes them rivers, in the functional sense, is that they are coherent, directional, and persistent flows of fluid with properties distinct from those of the medium in which they are immersed. The hydrothermal vents that feed these plumes are fissures in the ocean floor located mainly along the mid-ocean ridges, where tectonic plates separate and allow magma to approach the rocky surface. Seawater that penetrates the fissures of the oceanic crust is heated by geothermal heat, dissolves minerals from the surrounding rock, and emerges at the vents with temperatures that can range from 60 degrees Celsius in low-temperature vents to over 400 degrees Celsius in black smokers, high-temperature black chimneys. At a depth of 2,000 meters, the pressure is sufficient to keep this water in a liquid state even at temperatures that would be well above the boiling point at the surface. When this superheated and mineral-laden water emerges from a chimney into the cold bottom, it is much less dense than the surrounding water and rises. But it doesn't just rise. As it rises, it drags surrounding water with it in increasing turbulence, in a process called entrainment, and the resulting mixture progressively dilutes the concentrations of chemical compounds as the plume ascends. As it rises and mixes, the plume also cools. Eventually, it finds a depth where its density equals that of the surrounding oceanic water and loses its upward force. At this point, called the level of neutral buoyancy, the plume stops rising and spreads horizontally, creating a layer of water with a distinct chemical composition that can extend for hundreds or thousands of kilometers in all directions from the source. The black smokers, the most dramatic chimneys, build structures of precipitated sulfides that can grow at several meters per year, forming rocky towers and mushrooms of iron, zinc, and copper sulfide that accumulate around the emission mouths. The black cloud that gives the phenomenon its name is not smoke but fine particles of metal sulfides that precipitate from the hot water as it mixes with the cold bottom water. It is a natural industrial chimney, operating through geochemistry rather than combustion. The ocean floor is cut by tectonic scars that can extend for more than 4,000 kilometers. There is a class of structures at the bottom of the ocean that, if the sea were to evaporate and we were to walk around the planet, would be immediately identified as the most impressive topographical features ever seen. They are deep valleys, sometimes with vertical walls several kilometers high, that cut the ocean floor in straight or slightly curved lines for distances that rival the width of continents. They are not canyons carved by erosion. They are not rifts where magma rises. They are scars, the permanent record of where two tectonic plates slid against each other and then separated, leaving engraved in the oceanic rock the history of movements that occurred tens of millions of years ago. Fracture zones form along transform faults, the third type of boundary between tectonic plates, where plates neither collide nor separate, but slide laterally relative to each other. Mid-ocean ridges, the underwater mountain ranges where new oceanic crust is created, are not continuous structures. They are divided into segments by transform faults that displace them laterally, sometimes by hundreds of kilometers. When the plates move, the ridge segments continuously produce new crust, but the transform fault between them is a place of friction, earthquakes, and intense deformation. What remains after this active zone is left behind. When the plates move and the transform fault stops being an active boundary, is the fracture zone, the fossilized scar of a slide that lasted millions of years. The Mendocino Fracture Zone, off the coast of California, extends for more than 4,000 kilometers from the American coast toward the Central Pacific. On the north side of the fracture, the ocean floor is between 800 and 1,200 meters shallower than on the south side, because the northern crust is younger and has not yet cooled and sunk as much as the southern crust. The difference in depth creates an underwater escarpment, a wall that runs for 4,000 kilometers and which, if it were on land, would be one of the most spectacular features of the planet's topography. The Clipperton Zone and the Clarion Zone, in the eastern Pacific off Mexico, extend for more than 5,300 kilometers from their origins in the ridges to the depths of the Pacific. Within these zones, the geology is dense and varied. The escarpment walls expose cross-sections of the oceanic crust, accumulated over millions of years, layers of basalt of different ages that researchers sample with dredges and drill holes to reconstruct the history of plate movement. The deep valleys between the fracture zone walls accumulate sediments that include volcanic ash from distant eruptions, cosmic dust from meteorites, and the microfossils of organisms that lived in the waters above throughout the millions of years of deposition. Every meter of sediment accumulated at the bottom of a fracture zone is a slice of geological time, a library of events that occurred while the plates moved and the fracture walls bore witness. Sea floor sediments contain ash from eruptions that occurred millions of years ago, preserved as datable layers. The ocean floor is the most complete climatic and geological archive the planet maintains. Continents are places of erosion. Mountains wear down, plains are reworked by rivers, glaciers scrape and redistribute sediments, and the history recorded in continental rocks has gaps, distortions, and destructions that make interpretation incomplete. The ocean floor, by comparison, is a place of continuous deposition. Dust, microscopic shells of foraminifera and radiolarians, organic particles, and volcanic ash fall silently across the entire extent of the ocean, accumulate in layers that follow chronological order with remarkable fidelity, and stay there for tens to hundreds of millions of years without significant disturbance. Volcanic ash layers, called tephras or tephra layers, are the most precise time markings that exist in these sediments. Every large volcanic eruption injects a cloud of glassy particles of a specific chemical composition into the atmosphere, which distributes across the entire planet within weeks. As the particles settle into the ocean, they form a layer of measurable thickness covering areas of thousands to millions of square kilometers, depending on the magnitude of the eruption and wind patterns at the time. This layer has a unique geochemical signature, a fingerprint of isotopes and minerals that unequivocally identifies the eruption that produced it. Researchers who drill sediment cores from the ocean floor find these layers interspersed in the continuous sequence of deposition. A recent expedition in the Aegean Sea identified a thick white layer of pumice, glassy material of low density expelled in explosive eruptions, deposited between 510,000 and 530,000 years ago in multiple drilling sites separated by hundreds of kilometers. Geochemical analysis revealed that all samples had the same composition, confirming they were the product of a single eruption colossally larger than any other recorded in human history in that region, 6 times larger than the famous Minoan eruption that likely inspired the myth of Atlantis. The oldest ash preserved in oceanic sediments is more than 100 million years old. The Baltic Sea keeps in its sediments tephra layers from Scandinavian and Icelandic volcanoes with ages covering the last 10,000 years, each layer a date marked with precision in the sedimentary chronology. The deep oceans of the Pacific preserve eruptions from the Japanese island arc and the Mariana volcanoes that occurred tens of millions of years before the existence of any human being. Every large volcanic eruption in the planet's history that happened near oceanic coasts, or whose ash clouds reached the ocean, is fossilized somewhere in this sedimentary archive. For climate science, these layers are incomparable calibration instruments. Since each tephra can be precisely dated by isotopic methods, it provides chronological anchor points that allow for the exact dating of all other sediments above and below. Variations in temperature, salinity, ocean chemical composition, and atmospheric circulation. All this is recorded in the characteristics of the sediments between the ash layers. The volcano that 500,000 years ago launched ash over the eastern Mediterranean inadvertently marked on the oceanic calendar a precise moment from which oceanographers can measure the planet's climatic history in both directions of time. There are about 20 million tons of gold dissolved in the ocean, enough to give kilograms to every person on Earth, but in a concentration too low to extract. Gold has fascinated human beings with a consistency that spans civilizations and millennia without interruption. Egyptians, Romans, Aztecs, European colonial empires, and modern financial markets. The attraction to this yellow metal is one of the few constants in human history. And while entire peoples organized expeditions, wars, and empires around gold deposits measured in tons, there was an amount that no conqueror considered and no mine could rival, resting dissolved in the waters of all the planet's oceans. Approximately 20 million tons of gold, enough to give approximately 4 to 9 kilograms to every living human being. The origin of this oceanic gold is multiple. The erosion of continental rocks containing dissolved gold releases gold ions into the rivers, which carry them to the ocean. Hydrothermal vents on the seafloor dissolve gold from the oceanic crust and release it into the water. Winds carry dust particles containing traces of gold from deserts and continental soils to the ocean surface, where they gradually dissolve. Over billions of years, these tiny inputs accumulated in the oceans until reaching the concentrations present today. But the concentration is of a dilution that defies intuition. With the total amount of 20 million tons distributed through the 1.335 billion cubic kilometers of oceanic water, the concentration results in approximately 13 parts of gold per trillion parts of water, or about 13 nanograms per liter. 1 liter of seawater contains 13 billionths of a gram of gold. To collect a single gram of gold, it would be necessary to process approximately 77 million liters of seawater, the equivalent of 1.5 Olympic swimming pools. For a kilogram, 77 billion liters would be required. The fascination with extracting gold from the ocean is not new. Fritz Haber, the German chemist who invented the Haber-Bosch process for nitrogen fixation and who is frequently credited with having saved billions of lives by making the production of synthetic fertilizers viable, spent years after the First World War trying to extract gold from the ocean to pay Germany's war reparations. Haber was one of the greatest living chemists of his time. His laboratory developed increasingly sensitive methods to detect and concentrate the gold from seawater. And what the experiments were progressively revealing was that the original concentration estimates were wrong on the high side by 1 or 2 orders of magnitude. There was much less gold than the first measurements indicated, and what existed was in concentrations impossible to extract economically with any technology that existed or that Haber could imagine. Researchers have published studies in the journal Nature and the Journal of the American Chemical Society in recent years proposing extraction methods based on nanotechnology and highly selective absorber materials that could, in principle, concentrate gold from seawater more efficiently. But the economic problem remains unresolved. Extracting any substance dissolved in concentrations of nanograms per liter requires the processing of water volumes so astronomical that the energy cost of moving, filtering, and treating that water exceeds by many orders of magnitude the value of the recovered gold, even with ideal technologies. The Titanic is being devoured by a unique bacteria that consumes metal. The ship is expected to disappear completely in 20 to 30 years. The Titanic sank in the early hours of April 15, 1912, and reached the bottom of the North Atlantic at 3,800 meters deep in 2 large pieces, separated by about 600 meters, surrounded by a field of debris that spreads for kilometers. For decades, before Robert Ballard located it in 1985, the ship rested in the dark without human disturbance. And when the camera of the submersible finally illuminated it, what appeared was an image that combined grandeur and decadence. The bow still majestic, the famous staircase gone but the external structure relatively intact, covered in reddish structures that grew like oxidized stalactites across the entire surface of the hull. These structures were called rusticles, a neologism created by Ballard. Rust stalagmites, but not common rust. They are biogenic formations, built by communities of microorganisms that metabolize the iron of the hull. And in the center of these communities was identified, in 2010, the bacteria that is, slowly and inexorably, consuming the Titanic from the outside in Halomonas titanicae. Halomonas titanicae is a halophilic bacterium, which means it thrives in high salinity environments, and iron-trophic, which means it obtains metabolic energy from the oxidation of iron compounds. The mechanism is elegant in its minimalism. The bacteria converts ferrous iron, the reduced and soluble form of the metal that is released by the corrosion of steel, into ferric iron, the oxidized form. This reaction releases electrons that the bacteria uses as a source of energy for its metabolism. It is chemosynthesis at the simplest level, chemical energy extracted from an inorganic reaction. The result for the ship is an accelerated biochemical corrosion. The rusticles that grow on the surface of the hull look solid but are structurally fragile, with the interior being actively consumed by the bacterial colony that inhabits them. As the iron is progressively removed from the steel, the structural strength of the metal decreases. Hull plates that still seemed firm in the first submersible expeditions have already collapsed in later expeditions. The The stern, the section that suffered most from the impact when sinking, is in a more advanced state of deterioration. The distinction between the ship that is possible and the ship that exists is narrowing every year. The estimates of the time until complete disappearance vary among specialists. Some speak of 2030, others of 2040 to 2050, others in a few decades beyond that. The uncertainty reflects that the process is not linear and that it depends on variables difficult to measure. Density of bacterial colonies in different parts of the ship, exact temperature of the water at the bottom, interference from other species in the ecosystem that grew around the wreck. What the specialists agree on is that the process is irreversible and that the time frame is decades, not centuries. The most famous shipwreck in the world is on a microbiological countdown clock, and Halomonas Titanicae has no knowledge or interest in the history it is destroying. Champagne bottles of nearly 200 years found in shipwrecks in the Baltic Sea were still perfectly preserved and drinkable. In the summer of 2010, Finnish divers exploring an unidentified shipwreck in the Baltic Sea near the Åland Islands, between Finland and Sweden, brought to the surface a bottle of unusual shape from one of the most unexpected cellars that exist. When they opened the bottle still on the boat, they heard the characteristic sound of champagne and were greeted by an aroma that none of those present had experienced before. A champagne with more than 2 centuries of history, with notes of tobacco, oak, and an intense sweetness, completely intact, with the bubbles still present. The bottle had spent 200 years at the bottom of the Baltic, and it was better than most wines available in any cellar in the world. The wreck contained 168 bottles of champagne and an amount of beer, besides other objects that helped to date the cargo. The analysis of the bottles and the producing houses, identified as Huglar and Vuv Klikwat, besides artifacts found on board, put the probable date of the sinking between 1800 and 1830. The most probable hypothesis is that the ship carried a luxury cargo destined for the Russian nobility, a frequent trade in the Baltic in that period when French champagne was the sign of distinction par excellence in the Eastern European courts. The ship sank, the cargo went to the bottom, and the bottles stayed there for 2 centuries until the Finnish divers found them. The conditions at the bottom of the Baltic where the ship rested were, accidentally, perfect for the preservation of the wine. The water was at a constant temperature of about 4 degrees Celsius, the ideal temperature for wine storage. The darkness was total, eliminating any degradation by light. The pressure at 50 meters deep kept the corks firmly compressed, without vibration or mechanical movement that disturbs wine in poorly stored bottles. And the Baltic, with its low salinity and its particular chemical composition, has much lower rates of corrosion and decomposition than the tropical oceans. The accidental cellar created by the sinking was, in every parameter relevant to the preservation of the wine, superior to any cellar built by human beings. The Finnish team, after confirming the drinkability, called French champagne specialists for formal analysis. Samples from each producing house were opened for organoleptic and chemical analysis, and the results confirmed not only the authenticity but the preserved quality. An invited sommelier described the Vuv Klikwat of the shipwreck as having a complexity that modern champagnes rarely achieve, a consequence of years of slow development in perfect anaerobic conditions that created flavor compounds that no conventional cellar aging process reproduces. In 2024, the Baltic Tech Organization reported the discovery of another shipwreck in the Baltic Sea, this time with 100 bottles of 19th century champagne still intact, carefully packed in straw boxes that protected them during 2 centuries of rest. The leader of the expedition described never having seen anything like it in 40 years of shipwreck diving. The consulted specialists expressed confidence that the champagne would still be drinkable. The destination of the bottles remained undefined while underwater archaeologists were called to assess the proper extraction. There is a giant bronze statue of Jesus submerged off the coast of Italy, the most visited in the Mediterranean. In the Bay of San Frutuoso, between the villages of Portofino and Camogli on the Italian Riviera Ligure, at 17 meters deep and 300 meters from the coast, rests on the bottom of the Mediterranean one of the most singular images that the ocean holds in any part of the world. A bronze statue 2.5 meters tall representing Jesus Christ with arms raised toward the surface, eyes turned upward, the posture evoking at the same time supplication and blessing. The Cristo degli Abissi, Christ of the Abyss in English, was created by the Italian sculptor Guido Galletti and submerged at the site in 1954. The origin of the project is personal and touching. The diver Duilio Marcanti, considered the father of diving education in Italy, wanted to create a tribute to his friend Dario Gonzatti, the first Italian to use autonomous diving equipment, who died of a heart attack while diving in exactly that region of the Mediterranean in 1947. Marcanti conceived not only a memorial but a place, underwater, where divers could meditate and feel the presence of the sacred inside the element in which Gonzatti had died. The bronze with which the statue was cast was not bought. It was donated. Medals of Italian soldiers killed in the Second World War, cannons and parts of sunken ships, metal that had been part of war and death transformed into a statue of peace and protection. When the statue was submerged, Pope Pius XII sent his special blessing and a medal that still today rests at the feet of the statue. In 2014, Pope Francis sent another medal commemorating the 60th anniversary of the installation. In the 70 years since its placement, the statue has become the most frequented diving point of the Mediterranean. The depth of 17 meters makes it accessible to recreational divers of any skill level, and the clarity of the water of the Bay of San Frutuoso allows the statue to be visible from the surface in conditions of good visibility, attracting even kayakers and paddleboarders who approach from above. The Abbey of San Frutuoso, a medieval monastery that sits on the nearest beach, maintains a copy of the statue above the water, dedicated to those who lost themselves at sea. The statue has suffered with time. When it was originally installed, the surface of the bronze was clean and sharp. Over the decades, the incrustation of marine organisms and the corrosion of the bronze were progressively covering the details. The original cleaning method, which consisted of scrubbing the surface with metal brushes to remove barnacles and algae, caused irreparable damage to the patina of the bronze, creating microcracks that facilitated colonization by more organisms. In August 2025, divers from the Italian police used high-pressure water jets instead of brushes to clean the statue, a change of method that preserves the metallic surface while removing the encrustants biologically. Pirates used eye patches to keep one eye adapted to darkness, not necessarily to cover a wounded eye. The image of the pirate with an eye patch is so consolidated in popular culture that it seems inseparable from the archetype. From Captain Hook to Long John Silver, from Barbarossa to Captain Jack Sparrow, the eye patch is the most recognizable pirate accessory after the hat and the parrot. And the explanation that most people accept without questioning is that the eye patch covers a lost eye, a battle wound, a scar from the violent life at sea. This explanation is possible and, in some historical cases, certainly true. But there is another hypothesis, supported by the basic neuroscience of vision, which suggests that many eye patches had a completely different and much more strategic function. The phenomenon involved is called dark adaptation. When you go out from a lit environment to a dark environment, you see almost nothing in the first seconds or minutes. Gradually, as the rods of the retina, the photoreceptors specialized for low luminosity, recover their sensitivity after having been suppressed by the excess of light, the vision in darkness improves. The process is progressive and takes between 20 and 40 minutes to reach its maximum sensitivity. During this period, a human being in a dark environment is temporarily vulnerable. They can be seen and cannot see. For pirates whose survival depended on combat, boarding enemy ships, and navigating and fighting in conditions of variable light, this 20 to 40-minute window could be the difference between controlling the situation and being killed during the transition. A ship's deck illuminated by sunlight is an environment of high intensity. The interior of a ship, below the deck, is practically dark even during the day. And during a nighttime boarding, the difference between being on the surface illuminated by the moon and plunging through the hatch into the interior of an enemy ship is the difference between moderate light and almost total darkness. According to researchers who studied the navigation and combat habits of the 17th and 18th centuries, experienced pirates would use the eye patch not to cover a lost eye but to keep one eye permanently adapted to the darkness. The covered eye, deprived of light by the eye patch, maintains its retinal rods in a state of high sensitivity. The uncovered eye functions normally in lit environments. When the pirate needed to go down to the dark interior of the ship, to fight below the deck, to navigate in spaces without lighting, it was enough to transfer the eye patch to the other eye. The one that was covered was ready for the darkness immediately, without the 20 minutes of waiting for adaptation. It is a tactical vision strategy that does not require any technology besides a piece of leather or cloth tied over an eye. And that reflects, when you think about the real conditions of a ship boarding in the 17th century, a level of functional pragmatism that the pirates of reality had and that the pirate of cinema, with their permanently decorative eye patch, never demonstrates. This use of the eye patch does not invalidate the possibility that many real pirates also used it because of injury, but it adds a layer of interpretation that transforms a symbol of battle mutilation into an instrument of deliberate sensory adaptation, which is, ironically, much more pirate than any wound. The Arctic is losing its polar characteristics and becoming chemically similar to the Atlantic. The Arctic Ocean is the newest sea on the planet. It is the last to have been opened by plate tectonics, with the separation of Eurasia from North America creating an ocean basin that only began to fill approximately 50 million years ago. Throughout all its history, it maintained a distinct identity. Cold water, low salinity, strong stratification caused by sea ice that rejects salt when freezing, low biological productivity, and a circulation dominated by freshwater from ice melt and the Siberian and Canadian rivers that feed it. This profile is changing. Since approximately 2005, scientists observed a transformation called Atlantification. Water from the North Atlantic, warmer, saltier, and richer in nutrients, is invading the Arctic in volumes and at depths that were never seen before. The Atlantic water enters through the Fram Strait between Greenland and Svalbard, and through the Barents Sea, and is reaching deeper and deeper into the Arctic water column, eroding the haline stratification that historically separated the cold and fresh surface layers from the more saline and warmer deep waters. The primary cause is the loss of sea ice. The ice that forms on the surface rejects salt, creating a surface layer of freshwater that floats over the denser deep waters. With less ice forming in winter due to higher temperatures, less salt is rejected, and the surface layer loses its capacity to stratify the ocean. This allows the warm Atlantic water to penetrate more easily upwards, heating the surface layers and accelerating the melting of the residual ice even more. It is a positive feedback cycle. Less ice, more mixing, more Atlantic heat reaching the surface, even less ice. The consequences are multiple and profound. The biological productivity of the Arctic is increasing in some regions due to the nutrients brought by the Atlantic water, but the community of species is changing. Atlantic boreal species like cod and shrimp are expanding north, competing with the native Arctic species adapted to extreme cold. The thickness of sea ice is decreasing not only because of the higher temperature but because of the increased winter ventilation, when cold and dense surface waters sink and mix with the lower layers. And the heat transport to the Arctic is intensifying, with measurements showing Atlantic heat influxes doubling since 1990. The Arctic Report Card of 2025 described Atlantification as the dominant driver of ice loss in the central Arctic in the last 10 years, with impacts that extend to the efficiency of ocean mixing, carbon exchange, and primary productivity. The circulation of the transpolar drift is being altered, with implications for the transport of freshwater to the North Atlantic and potentially for the global climate. The Arctic is not only warming, it is transforming into a different ocean with chemistry, circulation, and ecology that increasingly look like the boreal Atlantic.